For over a century, one number has stood at the center of physics: 299,792,458 meters per second, the speed of light in a vacuum, the ultimate cosmic speed limit. The constant on which Einstein's entire framework of relativity was built, it's not constant. Or rather, it may not be in the way Einstein assumed. New measurements at the extreme edges of physics have begun to reveal something Einstein could not have tested. For over a century, one number has stood at the center of physics: 299,792,458 meters per second. The implications, if confirmed, would not refine modern physics. They would replace it. If you find yourself drawn to the questions that science is only now learning how to ask, do me a small favor and hit that like button and subscribe. It helps this channel continue, and every single one of you matters. Now, let's begin. There is a number at the foundation of modern physics that appears in equations describing electricity, magnetism, gravity, quantum mechanics, and the structure of space-time itself. It shows up in the formulas used to calculate the energy output of stars. It appears in the models describing the expansion of the universe from its earliest moments to its present state. It governs nuclear reactions, determines the relationship between mass and energy, and defines the geometry of spacetime at every scale that human beings have ever measured. It is the speed of light in a vacuum denoted by the letter c, and its value is exactly 299,792,458 meters per second. Not approximately, not the best exactly the definition. Because in 1983, the international scientific community decided to define the meter itself in terms of the distance light travels in a specific fraction of a second. The number is no longer subject to experimental refinement. It is fixed into the structure of measurement itself. This decision reflects something important. The confidence required to lock a constant into the very definition of a unit, to say, in effect, this number will never change, is not taken lightly in science, and that confidence is earned. The speed of light has been measured by more methods than almost any other quantity in the history of physics. In the 17th century, Euler Romer measured it by timing the eclipses of Jupiter's moons and noticing they ran ahead and behind schedule as Earth moved toward and away from Jupiter. In the 18th century, James Bradley measured stellar aberration, the slight shift in the apparent position of stars caused by Earth's orbital motion, and obtained a more accurate value. In the 19th century, Léon Foucault used rotating mirrors to measure light's speed directly in a laboratory, approaching the modern value closely. In the 20th century, laser interferometry brought the precision to better than 1 part per billion. Every method, every century, every independent approach, the same number emerged. The constancy of c has been tested across distances ranging from laboratory scales of a few meters to cosmological scales of billions of light years. It has been tested across time periods ranging from nanoseconds to the lifetime of the observable universe. It has been tested across energy ranges spanning many orders of magnitude. In every test, in every context, c has been found to be constant. Not approximately constant. Constant, and yet. The confidence in c as a truly fundamental constant rests on a theoretical framework that was completed before humanity had access to several categories of phenomena now within observational reach. Einstein's special relativity, which established c as the universal speed limit and the most fundamental constant in nature, was formulated in 1905. The experiments capable of probing the behavior of light at the highest energies across the longest distances, at the shortest length scales, and in the strongest gravitational fields simply did not exist in 1905. Many barely exist now, and as those extreme regimes have gradually become accessible, physicists have been asking a specific question with growing urgency. Is c truly constant at every scale and every energy? Or does the constant that built modern physics have a structure beneath it that Einstein's equations could not see? This question is not about whether relativity is wrong. Relativity is spectacularly, confirmedly right across every domain that has been experimentally tested. The question is whether relativity is complete, whether c is the deepest constant in nature, or whether it is the large-scale, low-energy manifestation of something more fundamental, operating at scales and energies beyond what the theory was designed to describe. The answer to this question is not yet known, but the pursuit of it has produced some of the most extraordinary physics of the last several decades, and the possibility that c may eventually be revealed as emergent rather than fundamental is not fringe speculation. It is the serious, peer-reviewed, institutionally funded work of physicists at the very frontier of the field. What drives this inquiry is not doubt about the measurements. Every measurement of C that has ever been made is correct. The doubt, if it can be called that, is about the domain. Every physical law ever written has eventually been found to describe a specific regime rather than all of reality. Newtonian mechanics described the regime of low velocities and weak gravity with extraordinary accuracy, and failed at high velocities and strong gravity. Classical thermodynamics described the macroscopic behavior of heat and work with great precision, and failed when the atomic scale was reached. Each theory was true. Each was complete within its domain. Each was eventually superseded by something deeper that contained it as a limiting case. There is no physical reason, theoretical or experimental, to believe that special relativity is the first theory in history exempt from this pattern. And if it is not exempt, then C, the constant at its centre, is the first place to look for the boundary. The named speed of light is, in an important sense, misleading. It suggests that C is primarily a property of light, a description of how fast photons happen to move through empty space. This description is accurate but profoundly incomplete. The deeper significance of C has nothing to do with light specifically. It is that C is the conversion factor between space and time in the geometry of space-time, the maximum rate at which any causal influence can propagate through the universe, and the fundamental constant that governs the relationship between mass and energy in Einstein's most famous equation. Light happens to travel at C not because of anything special about light itself, but because light is massless, and massless particles always travel at the universal maximum speed that the geometry of space-time permits. If photons did not exist, the constant C would still exist, embedded in the structure of space and time governing the maximum speed of every possible interaction. This distinction matters enormously for understanding what a hidden limit in the speed of light would actually mean in practice. If C were merely the speed of photons, a property of the electromagnetic field, then a deviation in C would be a statement about photons and electromagnetism. Interesting, certainly, but contained in its implications. If C is instead the geometric conversion factor between space and time, the more fundamental interpretation, then any deviation in C would be a statement about the geometry of space-time itself. It would mean that space-time has a structure at some scale that is different from the smooth, continuous geometry that both special and general relativity describe. It would mean that the equations governing the universe at the deepest level currently accessible are approximations to something more fundamental, something whose character physics is not yet determined. The distinction between these two interpretations, C as photon speed versus C as geometric constant, sits at the heart of why the possibility of a hidden limit is taken seriously by a significant portion of the theoretical physics community. If the hidden limit is real, it is not a statement about light. It is a statement about the nature of space and time at scales no experiment has ever directly probed. That is the kind of statement that changes not just one equation, but the entire conceptual foundation on which modern physics is constructed. To understand why this possibility exists, and specifically why Einstein's work left it open, it is necessary to understand what Einstein's framework actually assumes. Special relativity assumes that spacetime is a smooth, continuous mathematical manifold at all scales, that the geometry of the universe is the same whether you are examining it at the scale of galaxies or at scales far smaller than any particle. General relativity extends this to include curvature caused by mass and energy, but retains the smoothness assumption at every scale. Both theories have been tested extensively at scales accessible to current experiments, distances from fractions of a millimetre to billions of light years, and energies from the lowest measurable to the highest accessible in particle accelerators. Neither theory has been tested at the Planck scale, the fundamental length at which quantum effects on spacetime geometry itself are expected to become significant. And it is precisely at the Planck scale that the hidden limit, if it exists, is predicted to reside. The Planck scale is not a small extrapolation beyond current experiments. It is an almost incomprehensible distance into the unknown. The Planck length, the fundamental unit of length at which space-time quantum effects become order unity, is approximately 1.6 times 10 to the negative 35th meters. A proton is approximately 10 to the negative 15th meters across. The gap between a proton and the Planck length is 20 orders of magnitude, the same ratio as the distance between a single proton and the entire observable universe. No experiment, no particle accelerator, no conceivable laboratory instrument has ever probed physics at the Planck scale directly. The smooth space-time that Einstein assumed, and that all of physics since him has assumed, has never been verified at those depths. The assumption is reasonable, it is well motivated, it is supported by every measurement ever made at accessible scales, but it is still an assumption, and physics has learned, repeatedly and painfully, that its most comfortable assumptions are exactly where the deepest surprises hide. The speed of light, as a property of space-time geometry, will reflect whatever is true about space-time at its deepest level. If space-time is smooth all the way down, c is a perfect constant. If space-time has structure at the Planck scale that the smooth geometry approximates, c is an emergent effective constant, accurate at every scale we have ever measured, modified at the scale we have never reached. These are not two equally arbitrary possibilities. They are the two outcomes of the same fundamental question, and the answer will determine what kind of universe this actually is. In 1905, Albert Einstein published a paper titled On the Electrodynamics of Moving Bodies. The paper was unusual in several respects. It contained no citations to previous experimental work, despite the fact that an enormous amount of experimental work was directly relevant to its conclusions. It made no reference to the Michelson-Morley experiment of 1887, which had already established that the speed of light appeared to be independent of Earth's motion through space, the result that had puzzled physics for nearly 2 decades. Einstein arrived at his conclusions by a different route entirely. Through careful thought about what the laws of physics would have to look like to be consistent across different frames of motion, and through a willingness to follow that logic wherever it led, regardless of how uncomfortable the destination turned out to be. The paper rested on 2 postulates. The first, the laws of physics are the same for all observers in uniform motion. There is no experiment that can identify a preferred state of rest, no frame of reference from which the universe looks fundamentally different than from any other inertial frame. The second, the speed of light in vacuum is the same for all observers, regardless of the motion of the source or the observer. Not approximately the same, exactly the same. A photon emitted from a source moving toward you at half the speed of light still arrives at c, not at c plus half c. A photon emitted from a source moving away from you still arrives at c, not at c minus something. These 2 postulates, taken together, had consequences that demolished the conceptual foundations of physics as it had existed since Newton. If c is the same for all observers regardless of their relative motion, and if the laws of physics are the same in all inertial frames, then the concepts of absolute simultaneity and absolute time, the bedrock of Newtonian mechanics for more than 2 centuries, cannot be correct. 2 events that are simultaneous in one reference frame are not simultaneous in another frame moving relative to the first. Time does not flow at a universal rate identical for all observers. It flows at different rates for observers in relative motion, in a precise and calculable way determined by their relative velocity and by c. The consequences cascaded through physics with extraordinary logical completeness. Moving clocks run slow, a moving clock ticks more slowly than an identical stationary clock, and the slower ticking is real, not an illusion. Moving objects are shorter in the direction of motion than identical stationary objects, and the shortening is real. Mass and energy are equivalent and interconvertible according to E equals mc squared, the most famous equation in the history of science, a direct consequence of the 2 postulates and nothing else. The speed of light is an absolute maximum. No massive object can be accelerated to c because doing so would require an infinite amount of energy, and no causal influence of any kind can propagate faster than c without violating the temporal ordering of cause and effect. Each of these predictions has been confirmed experimentally to extraordinary precision. Time dilation has been measured directly using atomic clocks flown on aircraft and satellites. The mass-energy equivalence has been verified in every nuclear reaction ever measured: fission, fusion, particle-antiparticle annihilation. The relativistic energy-momentum relation governs every calculation in particle physics, and particle accelerators function correctly because the calculations are correct. GPS satellites require relativistic corrections to operate. Without the corrections computed from the 2 postulates of special relativity, GPS position calculations would accumulate errors of several kilometers per day. The 2 postulates are among the most thoroughly confirmed propositions in the history of empirical science. What Einstein settled, with these 2 postulates and the theory they generated, was the fundamental incompatibility between classical mechanics and electromagnetism. The incompatibility had been recognized and deeply troubling for decades. Maxwell's equations, the equations describing electricity, magnetism, and electromagnetic waves, predicted a specific speed for electromagnetic radiation. But the equations did not say what this speed was measured relative to. Classical mechanics said it must be relative to some medium, the so-called luminiferous ether through which light was presumed to travel. The Michelson-Morley experiment found no evidence of this medium. Einstein's resolution was to abandon the medium entirely. The speed of light is not measured relative to any medium. It is a property of space-time itself, the same for every observer. The incompatibility dissolved because it had been based on a wrong assumption about the nature of space and time. What Einstein did not settle, because it lay beyond any scale he could have tested, beyond any scale that can even now be directly tested, is what space-time looks like at its deepest level. He assumed it is smooth. He assumed C is truly constant at every scale. These assumptions were not errors. They were reasonable, well-motivated, and consistent with all available evidence. They remain so today. The question is only whether they will remain so at scales physics has not yet reached. In the century following Einstein's 1905 paper, physicists have attempted to find the boundary of special relativity with extraordinary creativity and persistence. They have built machines that accelerate particles to within a billionth of a percent of the speed of light and measured every aspect of those particles' behavior to the precision limits of available instrumentation. They have placed atomic clocks on aircraft, on satellites, in gravitational fields of varying strengths, and compared their readings with identical clocks that remain stationary. They have measured the energy released in nuclear reactions with sufficient precision to verify E = mc squared to parts per million. They have used the equations of special relativity billions of times in calculations underlying technology that demonstrably functions as predicted. And in every case, the equations have survived without deviation. Particle accelerators represent perhaps the most demanding test. At the Large Hadron Collider, protons are accelerated to energies of 6.5 trillion electron volts, velocities so close to c that the difference is measured in parts per quadrillion. At these velocities, the relativistic effects are enormous. A proton at full LHC energy has a relativistic mass approximately 6,900 times its rest mass. Its internal clock, if it had one, would run approximately 6,900 times slower than a stationary proton's clock. The particle's behavior, its lifetime, its interactions, the products of its collisions with other protons, must be calculated using special relativistic equations, or the predictions are completely wrong. They are not wrong. Every calculation agrees with every measurement. Muons provide a particularly clean demonstration. Muons are produced in the upper atmosphere when cosmic rays, high-energy particles from space, collide with atmospheric nuclei at altitudes of 15 to 20 kilometers. A muon at rest has a lifetime of approximately 2.2 microseconds before decaying into an electron and two neutrinos. Traveling at roughly 0.999 of the speed of light, a muon could in principle cover only about 660 meters before decaying, far short of the 15 kilometers it needs to travel to reach sea level. Yet muon detectors at sea level record enormous fluxes of atmospheric muons. They arrive because time dilation extends their lifetime, in the muon's reference frame. In Earth's reference frame, the muon ages slowly because it moves fast. The factor of extension is exactly what special relativity predicts for 0.999 c. Not approximately. Exactly to the precision of measurement. GPS satellites provide the most practically consequential test. GPS functions by comparing the arrival times of signals from multiple satellites to calculate a receiver's position. For the system to work, the clocks aboard the satellites must be synchronized with clocks on the ground to an accuracy of about 20 nanoseconds. Two relativistic effects alter the satellite clock rates. Special relativistic time dilation, which slows the satellite clocks because they are moving at approximately 14,000 km per hour relative to Earth's surface, and general relativistic gravitational time dilation, which speeds the satellite clocks because they are in a weaker gravitational field than Earth's surface. The net effect is that satellite clocks run faster than surface clocks by about 38 microseconds per day, an enormous discrepancy at GPS precision levels. The GPS system compensates for this using the equations of special and general relativity. If the relativistic corrections were not applied, GPS position errors would accumulate at approximately 11 kilometers per day. The corrections are applied, GPS works, the equations of relativity are correct. The consistency of these results across such different experimental contexts, particle accelerators, muon detection, atomic clock comparisons, GPS calibration, nuclear energy measurements, establishes special relativity as one of the best tested physical theories in history. The confirmation is not of a single prediction from a single experiment. It is the simultaneous, independent confirmation of many different predictions in many different physical systems, all governed by the same two postulates and producing results that agree with calculation to the precision available. And yet the question of whether these equations have a boundary, a regime where they are no longer correct, is not answered by any of these tests. Every test has been performed at energy scales far below the Planck scale, at length scales far above the Planck length, at gravitational field strengths far below what occurs at the event horizons of black holes or at the Big Bang singularity. Every confirmation of special relativity is confirmation within a specific domain. The domain is vast by human standards. It covers essentially everything that human technology and human observation have ever directly measured. But it does not cover everything. And the history of physics, the long sequence of theories confirmed within their domain and then superseded at the boundary of that domain, provides no reason to assume that special relativity is the exception, the one theory that is not an approximation. The equations could not be broken within their domain. The question is where the domain ends. The phrase speed limit of the universe is used so often that it has become almost a cliché, and like most clichés, it is accurate in a superficial sense, while missing the deeper meaning entirely. A speed limit in the ordinary sense, the kind posted on highways, is an externally imposed constraint, a rule that describes how fast vehicles are permitted to travel regardless of how fast they could theoretically travel. It is regulatory. It can be changed by legislation. It can be violated by any driver willing to accept the consequences. The speed of light in physics is nothing like this. It is not a rule imposed on a universe that could otherwise behave differently. It is a feature of the geometric structure of space-time as fundamental to the universe's architecture as the number of spatial dimensions. To understand what this means precisely, it helps to think about how space-time geometry actually works. In special relativity, space and time are not separate independent entities. They are aspects of a single four-dimensional structure called space-time, and the geometry of this structure is described by the Minkowski metric, a mathematical rule for calculating distances in 4 dimensions that assigns a different sign to the time dimension than to the 3 space dimensions. This sign difference creates a fundamentally different kind of geometry from ordinary 3-dimensional Euclidean space. In Euclidean space, any direction is accessible. You can move north, south, east, west, up, down, or any combination. In Minkowski spacetime, not all directions are equivalent. Some directions through spacetime are time-like. They point more toward the future than toward space, and they are accessible to massive objects. Some directions are light-like. They sit exactly on the boundary between time-like and space-like, and they are the paths that massless particles follow. Some directions are space-like. They point more through space than through time, and they are not accessible to any physical object or signal. The speed limit c is not a maximum on the space-like directions. It is the marker that separates the time-like from the space-like. Objects moving slower than c follow time-like paths through space-time. Objects moving at exactly c follow light-like paths. The space-like paths, the faster-than-light paths, are not forbidden by some rule. They are geometrically inaccessible, in the same way that a direction pointing simultaneously north and south in ordinary space is geometrically inaccessible. There is no direction in ordinary 3-dimensional space that points simultaneously north and south. There is no path in Minkowski's spacetime that is simultaneously causal and faster than light. The constraint is geometric, not regulatory. This geometric understanding is what makes the possibility of a hidden limit conceptually significant in a way that goes far beyond any simple violation of the speed limit. If c is the marker that separates accessible from inaccessible paths through space-time geometry, if it is a property of the geometry itself, then any modification of c at some energy scale is a modification of space-time geometry at that scale. It would mean that the smooth, continuous Minkowski geometry of special relativity is an approximation, accurate at every scale that has been tested, but modified at scales that have not been tested. The hidden limit would not be a violation of the speed limit in the regulatory sense. It would be a revelation that the geometry from which the speed limit emerges has a more complex structure than the smooth manifold that special and general relativity assume. The analogy with refraction in optics is useful here. Light travels at c in perfect vacuum. In a transparent material, glass, water, diamond, it travels more slowly, Tc divided by the material's index of refraction. The index of refraction is itself a property of the material's structure at the atomic level, and in many materials it is frequency dependent. Different frequencies of light travel at slightly different speeds, which is why prisms separate white light into its spectral components. The vacuum, as quantum field theory reveals, is not empty. It is a sea of quantum fluctuations. If the quantum vacuum has a structure, as the Casimir effect and other measured phenomena demonstrate that it does, then it may have an effective index of refraction that is frequency dependent at energies approaching the Planck scale, in exactly the way that ordinary materials have frequency dependent indices of refraction. The hidden limit in this picture is not a violation of c. It is c being what c has always been, a property of the medium through which light travels, but with the medium turning out to have structure at depths never previously probed. This is the conceptual landscape within which the search for the hidden limit takes place, not a universe where the speed limit has been broken, a universe where the geometry that generates the speed limit turns out to be richer, deeper and more intricate than the smooth featureless manifold that has served physics so well for over a century. The vacuum of quantum field theory is one of the most counterintuitive concepts in the modern physics, and it is central to understanding why the speed of light might have a hidden energy-dependent structure. In classical physics, the vacuum is exactly what the word suggests, nothing. The absence of matter, energy, and all physical fields. A perfect emptiness in which the laws of physics are suspended because there is nothing for them to govern. This picture is wrong, and it has been known to be wrong since the development of quantum mechanics in the early 20th century. Quantum mechanics imposes a fundamental constraint on the precision with which complementary physical quantities can simultaneously be specified. Position and momentum, energy and time, these pairs of quantities are subject to the Heisenberg uncertainty principle, which states that the more precisely one member of a complementary pair is known, the less precisely the other can be known, not merely as a practical limitation of measurement, but as a fundamental feature of reality. For energy and time, the uncertainty principle implies that over sufficiently short timescales, the energy of any region of space is uncertain by an amount that grows as the timescale shrinks. This uncertainty is not a gap in knowledge. It is a physical fact, and it has physical consequences. The consequence in the context of the vacuum is that the energy of empty space is never precisely zero. At every point in space, at every moment in time, the energy fluctuates. Quantum fields briefly and spontaneously create particle-antiparticle pairs from the vacuum, which then annihilate and return their energy to the vacuum on timescales short enough to be consistent with the uncertainty principle. These virtual particles are not directly observable in the way that real particles are. They cannot be detected individually with particle detectors because they exist and disappear too quickly for direct interaction. But they are not merely theoretical constructs. Their effects on real, observable physical systems are measurable and have been measured with extraordinary precision. The most direct demonstration is the Casimir effect, predicted by the Dutch physicist Hendrik Casimir in 1948 and first measured with convincing accuracy by Steve Lamoreaux in 1997. The Casimir effect is an attractive force between two uncharged, electrically conducting plates placed very close together in an otherwise empty vacuum. By classical physics, two uncharged plates should exert no force on each other whatsoever. By quantum field theory, they must. The conducting plates impose boundary conditions on the electromagnetic vacuum fluctuations in the gap between them, only fluctuations whose wavelengths fit an integer number of half wavelengths into the gap are permitted between the plates. Outside the plates, no such restriction exists, and vacuum fluctuations of all wavelengths are present. The asymmetry between the restricted fluctuations inside and the unrestricted fluctuations outside creates a net pressure pushing the plates together. This pressure has been measured to better than 1% accuracy, and it matches the quantum field theory prediction precisely. The Lamb shift is another measurable consequence of vacuum fluctuations. In the hydrogen atom, the electron orbiting the nucleus has energy levels whose values are calculated from the interaction of the electron with the proton's electric field. In the absence of vacuum fluctuations, two specific energy levels, the two S1/2 and two P1/2 levels, would be exactly degenerate, having the same energy. In reality, they have slightly different energies, a discrepancy first measured by Willis-Lamb in 1947 and now called the Lamb shift. The shift arises because the electron's interaction with the vacuum fluctuations of the electromagnetic field slightly modifies the electron's apparent charge and mass, shifting the energy levels by an amount that can be calculated from quantum electrodynamics with extraordinary precision. The measured Lamb shift agrees with the quantum electrodynamics prediction to better than 12 significant figures, one of the most precise agreements between theory and experiment in all of science. These experiments establish beyond any reasonable doubt that the quantum vacuum is a physically active medium. It is not empty. It is populated by fluctuating quantum fields whose presence influences every physical process that occurs within it. For the question of whether the speed of light is truly constant, this established fact is crucial. A photon propagating through the quantum vacuum is not propagating through a featureless geometric backdrop. It is propagating through a medium whose quantum fluctuations it interacts with, a medium whose properties at very high energies approaching the Planck scale, may be different in ways that no current experiment has yet been able to probe. The vacuum that quantum field theory describes is the mechanism through which theories of quantum gravity predict that the speed of light might acquire a hidden energy dependence. The Casimir effect is not evidence of this energy dependence. It is evidence that the mechanism through which the energy dependence would operate is real. Consider what it actually means for a photon to travel from a gamma-ray burst to Earth across 7 billion light-years of space. In the classical picture, the picture that special relativity provides, the photon moves through a smooth, featureless, geometrically perfect vacuum at exactly c, undeflected, undelayed, and unchanged for the entire journey. 7 billion light-years. Approximately 66 trillion kilometers, traversed at the same speed as a photon crossing a laboratory bench. This is what the smooth spacetime of special relativity implies, and it is the baseline against which any hidden limit must be measured. What quantum gravity theories suggest is that this picture, while correct as an approximation, is not complete. The quantum vacuum through which the photon travels is not smooth or smooth at all scales. At the Planck length, approximately 1.6 times 10 to the negative 35th meters, the smooth geometry of spacetime is expected to give way to something qualitatively different. A fluctuating, possibly discrete structure, whose character has not yet been determined from first principles, because the theory of quantum gravity that would determine it does not yet exist in complete form. What does exist are candidate frameworks, loop quantum gravity, string theory, causal set theory, and others, each of which predicts a specific form of departure from smooth spacetime at the Planck scale, and each of which, in its own way, predicts that a photon propagating through this non-smooth structure does not propagate at exactly the same speed regardless of energy. The photon interacts with the Planck scale structure, and the interaction is energy dependent. The energy dependence arises from a simple and physically motivated argument. Every quantum particle has a de Broglie wavelength inversely proportional to its energy. A high-energy photon has a shorter wavelength than a low-energy photon. A photon whose wavelength is comparable to the scale of some structure in the medium through which it travels interacts more strongly with that structure than a photon whose wavelength is much longer than the structure scale. This is why visible light interacts strongly with features of ordinary materials at the atomic scale, while long-wavelength radio waves pass through the same materials essentially without interaction. Radio wavelengths are too long to resolve atomic scale structure. The Planck scale structure of spacetime, if it exists, presents the same physics at an incomparably smaller scale. Photons with wavelengths far longer than the Planck length, every photon ever detected, interact very weakly with the Planck scale structure. But higher energy photons have shorter wavelengths and interact slightly more strongly than lower energy photons. The difference in interaction strength produces a difference in propagation speed. The magnitude of this effect per unit distance of travel is extraordinarily small. At the Planck length scale, the predicted fractional difference in speed between a high energy and low energy photon is of order the photon energy divided by the Planck energy, a number that for any photon accessible to current detection is on the order of 10 to the negative 15 or smaller. Over any laboratory distance, this tiny fractional speed difference produces an unmeasurably small arrival time difference, but the photons from a gamma-ray burst do not travel laboratory distances. They travel 7 billion light-years, which contains approximately 10 to the 60th Planck lengths. Over this distance, even a fractional speed difference of 10 to the negative 20 produces a cumulative time delay of several seconds, a delay that, if present and cleanly separable from other effects, would be detectable with existing telescopes. This is the fundamental reason why gamma-ray bursts are the natural laboratory for testing the hidden limit. They produce photons spanning a vast range of energies, from kilo-electron-volt X-rays to giga-electron-volt gamma rays, a factor of 1,000,000 or more in energy. They produce these photons in bursts that last only milliseconds to seconds, providing a well-defined emission start time, and they occur at cosmological distances that amplify any tiny energy-dependent speed difference into a potentially measurable arrival time separation. The universe has arranged its most energetic explosions at its greatest distances and filled them with photons of wildly different energies, as if designing the ideal instrument for detecting the one effect that no laboratory on Earth could ever hope to measure. The photon that began its journey 7 billion years ago, in a cataclysmic explosion that outshone the galaxy that contained it, carries within the timing of its arrival information about the structure of space-time at scales 20 orders of magnitude smaller than itself. It does not know it is carrying this information. It simply arrives or fails to arrive exactly when it should, and the difference, if it is there, tells physics something that cannot be learned any other way. The universe, in this sense, is not just the object of study. It is the instrument through which the study is conducted. And no instrument built by human hands comes close to matching its sensitivity. The story of the Casimir effect begins not with an experiment but with a calculation performed in 1948 by the Dutch physicist Hendrik Casimir while working at Philips Research Laboratories in the Netherlands. Casimir had been thinking about the forces between colloidal particles, small particles suspended in a liquid medium, and in doing so was led to consider what quantum field theory predicts about the forces between two perfectly conducting metal plates held very close together in a vacuum. The calculation was not experimentally motivated, it was purely theoretical, and its result was something that, by any classical intuition, should have been impossible. Two electrically neutral plates, carrying no charge and no magnetic field, separated by a vacuum that contains nothing, should nevertheless attract each other with a force that could in principle be measured. The mechanism behind this attraction is the same one that makes the quantum vacuum physically active rather than empty. Quantum field theory describes the electromagnetic field not as a classical field that can be zero in the absence of charges and currents, but as a quantum field that has a ground state, a lowest possible energy state that is not zero. The ground state of the electromagnetic field in a region of space is filled with vacuum fluctuations, virtual photons constantly appearing and disappearing in accordance with the Heisenberg energy-time uncertainty relation. These virtual photons have no definite wavelength. They span a continuous spectrum from zero wavelength to infinite wavelength. Their combined energy is the vacuum energy of the electromagnetic field, and it is formally infinite, a result that quantum field theory handles through renormalization, a mathematical procedure for extracting finite physical predictions from apparently infinite sums. When two conducting plates are placed parallel to each other at a small separation, they alter the boundary conditions for the electromagnetic vacuum fluctuations. A conducting surface requires the component of the electric field parallel to the surface to vanish at the surface. This boundary condition restricts which wavelengths of electromagnetic fluctuations are permitted in the gap between the plates. Only fluctuations whose half wavelengths fit an integer number of times into the gap are allowed, the same constraint that restricts which standing waves can form in a closed box. Outside the plates there is no such restriction, and fluctuations of all wavelengths are present. The energy density of vacuum fluctuations inside the gap is therefore lower than the energy density outside. More modes are permitted outside than inside. This energy density difference produces a net inward pressure on the plates, a force pulling them toward each other. The Casimir force. The predicted force is small. For two plates with area of 1 square centimetre separated by 1 micrometre, the Casimir force is approximately 1/10,000th of a newton, comparable to the weight of a water droplet 1/10 of a millimetre in diameter. Measuring such a force required instrumentation that did not exist when Casimir first predicted it, and the first convincing measurements were not made until 1997, nearly 50 years after the prediction. Steve Lamoureux at the University of Washington used a torsion pendulum to measure the Casimir force between a flat plate and a sphere, a geometry more amenable to precise calculation than two parallel plates, and obtained agreement with the theoretical prediction at the 1% level. Subsequent experiments using atomic force microscopy have confirmed the Casimir force with even higher precision. The implications for the speed of light question are important precisely because the Casimir effect is not theoretical. It has been measured. It provides direct, unambiguous experimental evidence that the quantum vacuum is a physically real medium, that its fluctuations exert measurable forces on physical objects, and that the properties of this medium, specifically the spectrum of allowed fluctuations, can be modified by boundary conditions. If boundary conditions imposed by conducting plates can modify the vacuum fluctuation spectrum enough to produce a measurable force, then conditions at the Planck scale, where space-time geometry itself imposes boundary conditions on quantum fields, might modify the propagation of photons in ways that, while individually tiny, accumulate over cosmological distances into detectable effects. The Casimir effect does not prove that the speed of light has an energy-dependent limit. It proves that the mechanism by which such a limit would arise, the physical reality and susceptibility to modification of the quantum vacuum, is not theoretical. It is experimentally verified. The path from the Casimir effect to the hidden limit on the speed of light is not short or direct, but it is real. The vacuum that pushes conducting plates together with a measurable force is the same vacuum through which every photon in the universe travels. Understanding that this vacuum is not empty, that it is a medium with structure and physical properties, is the first step toward understanding why the speed of light through this medium might not be perfectly constant at every energy, across every distance, at every scale that physics might eventually reach. Among the foundational results of modern physics, the masslessness of the photon holds a special place. It is not merely an experimental observation, a measurement that found the photon mass to be zero within some experimental uncertainty. It is a theoretical necessity embedded in the mathematical structure of quantum electrodynamics through the concept of gauge symmetry. The electromagnetic field is described by a gauge theory, a theory with a specific mathematical symmetry under which the field can be transformed in certain ways without affecting any physically measurable quantity. The masslessness of the photon in this framework is a direct consequence of this gauge symmetry. A massive photon would require breaking the gauge symmetry of electromagnetism, which would in turn destroy the mathematical consistency of quantum electrodynamics and alter the long-range, infinite-distance nature of the electromagnetic force. The photon is massless because electromagnetism has its specific mathematical structure, and this structure has been verified in countless experiments over many decades. And yet, from a purely experimental standpoint, the photon mass cannot be measured to be exactly zero. No measurement can establish an exact zero for any quantity. A measurement of zero is always a statement that the quantity is smaller than the measurement's precision, not that it's precisely zero. Current experimental upper limits on the photon mass place it below to approximately 10 to the negative 54th kilograms, a number so extraordinarily small that it is, for any practical physical calculation, indistinguishable from zero. For comparison, the electron, the lightest known massive particle, has a mass of approximately 9 times 10 to the negative 31st kilograms, 23 orders of magnitude larger than the upper limit on the photon mass. The photon is, for all practical purposes, massless. But the theoretical possibility of a tiny but non-zero mass has not been experimentally eliminated, and this possibility has interesting connections to the question of the speed of light. If the photon had a mass, even an immeasurably small mass, the behavior of light would differ from the predictions of standard massless electrodynamics in several ways. The most relevant for the hidden limit question is the energy dependence of the photon speed. A massless photon always travels at exactly c regardless of its energy. This is a direct consequence of masslessness in special relativity. A massive photon, however, travels at a speed that depends on its energy. The speed approaches c asymptotically as the energy increases relative to the rest mass energy, but for photons with energies comparable to their rest mass energy, the speed can be significantly less than c. For photons with energies much greater than their rest mass energy, which is the situation for every photon ever detected, given how small the photon mass upper limit is, the difference between the photon speed and c scales as the rest mass energy squared divided by twice the photon energy squared. The higher the photon energy, the closer its speed is to c. This produces a specific identifiable signature. High-energy photons from distant sources would arrive slightly before low-energy photons from the same source. The photon mass-induced speed difference has the opposite sign from the speed difference predicted by most quantum gravity models, in which higher-energy photons interact more with the Planck scale structure and therefore travel slightly more slowly. This opposite sign is useful observationally, because it means that comparing the arrival time differences of high-energy and low-energy photons from gamma-ray bursts can simultaneously constrain both photon mass and quantum gravity modifications, with the two effects being distinguishable by the direction of the time delay, which energy arrives first. The current constraints on photon mass from astrophysical observations are stronger in some respects than laboratory measurements. The absence of detectable dispersion in the arrival times of photons of different energies from distant gamma-ray bursts places limits on the photon mass that are competitive with or better than laboratory bounds. Radio observations of pulsars, whose emission spans a wide range of radio frequencies, also constrain the photon mass through the absence of detectable frequency-dependent arrival time differences beyond what is accounted for by the known dispersive effect of the interstellar ionized medium. The photon mass question illustrates a broader theme in the search for the hidden limit. Multiple independent physical mechanisms, quantum gravity modifications, non-zero photon mass, dark photon mixing, variations in fundamental constants, can all in principle produce energy-dependent modifications to the speed of light, but each produces a specific functional form and a specific sign of the effect. The observational program is therefore not simply a search for any deviation from a constant c. It is a program of precision measurement sensitive enough to distinguish between specific functional forms to determine both whether an effect is present and, if it is, which mechanism is responsible. The photon mass question is one thread in this larger tapestry. Lorentz invariance is the mathematical symmetry that lies at the heart of special relativity. Named for the Dutch physicist Hendrik Lorentz, who derived the transformation equations that bear his name before Einstein provided their physical interpretation. Lorentz invariance states that the laws of physics take the same mathematical form in all inertial reference frames, all frames of reference that are either at rest or moving at constant velocity relative to some other frame. More precisely, Lorentz invariance requires that physical laws are invariant under Lorentz transformations, the specific mathematical transformations that relate the coordinates of an event in one inertial frame to the coordinates of the same event in another inertial frame, moving at constant velocity relative to the first. These transformations are parameterized by the velocity of relative motion and by a single universal constant, the speed of light. The universal role of c in Lorentz transformations is what makes the constancy of the speed of light a consequence of Lorentz invariance rather than an independent assumption. If the laws of physics are Lorentz invariant, then c, the parameter that appears in the Lorentz transformations, must be the same in all inertial frames. An observer measuring the speed of light in one frame finds exactly c. An observer in a frame moving at 99% of c relative to the first frame also measures exactly c. An observer moving toward the light source or away from it or at any angle to it measures exactly c. This is not because light is special. It is because any massless field propagating in a Lorentz invariant spacetime necessarily propagates at exactly c. The constancy of the speed of light is a geometric consequence of the symmetry of spacetime, not a property of photons specifically. What Lorentz invariance requires, stated precisely, is that no experiment can identify a preferred reference frame, a frame in which the laws of physics take a simpler or more fundamental form than in any other inertial frame. This is a statement of profound democratic equality among reference frames. The universe has no center, no preferred direction, no preferred state of rest. The vacuum of spacetime looks the same in all directions and from all velocities. If Lorentz invariance is exact, then no physical measurement can ever reveal a preferred frame, no matter how sensitive the measurement or how extreme the conditions. The question of whether Lorentz invariance holds exactly at all energies is precisely the question of whether the hidden limit exists. If the speed of light has an energy dependence, if a photon with energy E travels at c times 1 minus some small correction proportional to some power of E divided by the Planck energy, then there is an energy scale that is physically preferred. The Planck energy is singled out by nature as the scale at which the correction becomes significant. This preferred scale defines a preferred reference frame, the frame in which the Planck scale has its full value rather than being Lorentz contracted or time-dilated. An energy-dependent speed of light is therefore not merely an interesting modification of photon behavior. It is, if it exists, a violation of the exact Lorentz invariance that special relativity requires. This is a significant conceptual point. The search for a hidden limit on the speed of light is equivalent to the search for Lorentz invariance violation at Planck scale energies. These are two descriptions of the same physics, and the Lorentz invariance violation framing is useful because it connects the hidden limit to a large and sophisticated experimental program. The systematic search for Lorentz invariance violation using every available physical system and every available experimental technique. This program, organized theoretically through a framework called the Standard Model Extension, developed by Alan Kosteletsky and collaborators, categorizes all possible Lorentz violating operators that could appear in the equations of physics, parameterizes their magnitude, and compiles experimental constraints on each parameter from every relevant observation. The constraints are extraordinarily tight at energies accessible to laboratory experiments. Atomic physics experiments, searching for directional anisotropies, tiny variations in atomic transition frequencies depending on the orientation of the experiment relative to some fixed direction in space, have placed upper limits on certain Lorentz invariance violation parameters at the level of 10 to the negative 33rd or smaller in natural units. These constraints mean that if Lorentz invariance is violated, it is violated at a level utterly invisible to laboratory physics. This is exactly what would be expected if the violation is suppressed by the Planck scale. At laboratory energies, the suppression factor is so enormous that no laboratory measurement can detect it. The absence of laboratory signals for Lorentz invariance violation is entirely consistent with, and in fact expected from, any theory in which Lorentz invariance is modified only at Planck scale energies. The absence of evidence at laboratory scales is not evidence of absence at Planck scales. The experimental search for Lorentz invariance violation, the search for evidence that the laws of physics are not exactly the same in all reference frames at all energies, is one of the broadest and most systematic programs in experimental physics. It spans multiple decades, multiple research groups, multiple experimental techniques, and multiple theoretical frameworks. It has produced the most precisely measured null results in the history of science, confirmation that Lorentz invariance holds to extraordinary precision across a wide range of physical systems and energy scales, and it has motivated a search for violations at energy scales inaccessible to laboratory experiments, but potentially accessible through astrophysical observations of the universe's most energetic phenomena. The laboratory-based component of the search uses physical systems whose properties are exquisitely sensitive to small departures from Lorentz invariance. Among the most powerful are experiments based on atomic clocks and optical resonators. An atomic clock measures time using the frequency of electromagnetic radiation absorbed in specific atomic transitions. These frequencies are determined by the quantum mechanics of the electromagnetic, which in turn depends on the electromagnetic interaction and the structure of space-time. If Lorentz invariance is violated, if there is a preferred direction in space at the fundamental level, the frequencies of atomic transitions might depend slightly on the orientation of the atom relative to this preferred direction. As Earth rotates and orbits the Sun, the orientation of any laboratory experiment relative to a cosmologically preferred direction changes, and atomic clock frequencies should oscillate slightly at the rotation and orbital frequencies if Lorentz invariance is violated. These oscillations have been searched for with extraordinary sensitivity. Experiments comparing the frequencies of different types of atomic clocks, hydrogen masers, cesium fountains, optical atomic clocks based on strontium, ytterbium, or aluminum, over periods of months to years, have found no evidence of any oscillation attributable to Lorentz invariance violation. The upper limits on the oscillation amplitudes, translated into constraints on Lorentz invariance violation parameters, are among the tightest in all of physics, constraining certain violation parameters to the level of 1 part in 10 to the 33rd or smaller. These are measurements of extraordinary delicacy, made possible by the development of optical atomic clocks that maintain frequency stability at the level of 1 part in 10 to the 18th over timescales of thousands of seconds. Optical resonator experiments provide complementary constraints. A resonator, an optical cavity defined by two mirrors facing each other, sustains a laser at a frequency determined by the cavity length and the speed of light within the cavity. If the speed of light is directionally dependent, if it is slightly faster in one direction than in the perpendicular direction, the frequencies of two perpendicular resonators would differ by an amount related to the degree of directional asymmetry. Experiments comparing the frequencies of perpendicular resonators with extraordinary sensitivity, as Earth's rotation changes the orientations relative to any preferred direction in space, have found no evidence of directional anisotropy. The constraints on direction-dependent light speed variations are at the level of a few parts in 10 to the 18th, meaning that if the speed of light is direction-dependent, the variation is smaller than a few parts in a billion. Beyond the laboratory, astrophysical tests of Lorentz invariance use the universe itself as an instrument with sensitivity impossible to achieve in any ground-based setup. The energy available in gamma-ray bursts, the distances over which photons propagate, and the broad energy ranges of detected photons make astrophysical observations sensitive to Lorentz invariance violations at Planck scale energies that are utterly invisible to laboratory measurements. The threshold energies for certain particle physics reactions, pair production, pion production, photon splitting, are sensitive to modifications of the energy-momentum relation that Lorentz invariance violations would produce. If the relation between a photon's energy and its momentum is modified in the specific way predicted by quantum gravity theories, the minimum energy required for certain reactions to occur would shift from its standard value. Observations of whether high-energy gamma rays interact with background radiation fields at the expected rates, whether pair production occurs at the expected threshold energies, provide constraints on these modifications. The results of all these experimental searches, taken together, paint a coherent picture. Lorentz invariance is an excellent approximation at all energy scales tested by laboratory physics. It is a good approximation at the highest energies accessible through cosmic ray and gamma ray burst observations, but the precision of the highest energy tests is not yet sufficient to detect effects suppressed by a single power of the ratio of the photon energy to the Planck energy, the level predicted by the most optimistic quantum gravity models. The experiments have confirmed that Lorentz invariance is not violated at scales far below the Planck scale. They have not yet achieved the sensitivity to confirm or deny violations at the Planck scale itself. The cosmic ray spectrum is one of the most remarkable features of the observable universe, and it represents one of the most important natural laboratories for testing physics at energies impossible to achieve by any human technology. Cosmic rays are charged particles, primarily protons and atomic nuclei with a small admixture of electrons and other species, that travel through space at velocities approaching the speed of light and bombard Earth's atmosphere continuously and isotropically from all directions. They were discovered by Victor Hess in 1912, who carried electroscopes aloft in a series of balloon flights and found that the ionization rate in the atmosphere increased with altitude, demonstrating that the ionizing radiation came from above, from space, rather than from Earth's radioactive crust. The discovery earned Hess the Nobel Prize in Physics in 1936. The energy spectrum of cosmic rays spans an astonishing range, from energies comparable to those of the highest energy particles produced by accelerators to energies more than 10 million times greater than anything the Large Hadron Collider can produce. At the highest energies, above about 10 to the 18th electron volts or 1 eV, individual cosmic ray particles carry kinetic energies comparable to those of a cricket ball moving at roughly 100 km per hour. This energy, concentrated in a single subatomic particle whose mass is less than 1/1000th of a gram, represents a density of kinetic energy per unit mass that dwarfs anything achievable by human technology by many orders of magnitude. How nature accelerates particles to such extreme energies is itself a major unsolved problem in astrophysics. At the highest energies, the cosmic ray spectrum shows several features that are sensitive to the physics of particle interactions at extreme energies, and therefore sensitive to any modification of those interactions by Lorentz invariance violation. The most important of these features is a suppression in the flux of the cosmic rays above approximately 50 eV, a suppression broadly consistent with the prediction of the Greisen-Zatsepin-Kuzmin cutoff, discussed in detail in the following section. A second feature is a change in the composition of cosmic rays with energy. The ratio of light nuclei, such as protons, to heavier nuclei, such as iron, changes with energy in a way that reflects the distance over which cosmic rays can propagate before losing energy and the composition of the sources from which they originate. Both of these features are sensitive to the physics of ultra-high energy particle interactions, and both would be modified if the energy-momentum relation for photons or protons is altered by Lorentz invariance violation. The detection of ultra-high energy cosmic rays requires enormous ground-based detector arrays because the flux at the highest energies is so low, approximately 1 particle per square kilometre per century above 100 eFedor, that individual detectors are completely inadequate. The Pierre Auger Observatory in Mendoza Province, Argentina covers 3,000 square kilometres of flat terrain with 1,660 water Cherenkov detector tanks, each containing 12 tons of ultra-pure water spaced 1.5 kilometres apart. When an ultra-high energy cosmic ray strikes the atmosphere, it produces an extensive air shower, a cascade of secondary particles that spreads across kilometres of atmosphere and reaches the ground over an area comparable to a city. The pattern of arrival times and particle densities at the Auger tanks allows reconstruction of the primary particle's energy and arrival direction with considerable precision. A companion set of fluorescence telescopes observes the nitrogen fluorescence emitted as the shower develops in the atmosphere, providing an independent energy measurement. The telescope array, located in Millard County, Utah, covers an area of approximately 700 square kilometers and provides Northern Hemisphere coverage complementary to Auger's Southern Hemisphere observations. Together, these observatories have detected thousands of events above 10 eV and dozens above 100 eV, events whose energies exceed the standard model predictions for what acceleration mechanisms can achieve in known astrophysical environments. The connection to the hidden limit is direct. If Lorentz invariance is violated at Planck scale energies in the way predicted by quantum gravity theories, the energy momentum relation for protons is modified, and the threshold energies for interactions with the cosmic microwave background are shifted from their standard values. The location, sharpness, and shape of the GZK suppression in the observed cosmic ray spectrum are therefore precision tests of the energy momentum relation at the highest energies accessible anywhere in the universe. They have not yet revealed any violation, but the constraints they place on Lorentz invariance violation parameters at ultra-high energies are among the strongest available from any source, complementing the constraints from gamma-ray burst observations at lower energies and from laboratory experiments at still lower energies. Each independent probe narrows the space of possible modifications, and together they form a growing net closing in on the Planck scale from multiple directions simultaneously. In 1966, 1 year after Arno Penzias and Robert Wilson discovered the cosmic microwave background radiation, 3 physicists independently realized that the discovery had an immediate and remarkable consequence for the highest energy cosmic rays. Kenneth Greisen at Cornell University and Vadim Zatsepin and Yuri Kuzmin at the Institute for Nuclear Research in Moscow each calculated what happens when an ultra-high energy proton propagates through the sea of background photons that fills all of the space. The calculation is a straightforward application of special relativistic kinematics and the known cross-sections for proton-photon interactions. Its prediction is called the Greisen-Zatsepin-Kuzmin cutoff, and it places a fundamental limit on how far the most energetic cosmic rays can travel. The mechanism is elegant in its simplicity. The cosmic microwave background fills all of space with photons at a temperature of approximately 2.7 Kelvin. In the rest frame of the universe, these photons have energies of approximately 0.0006 electron volts, far too low to interact significantly with anything. But consider the frame of reference of an ultra-high energy proton. In the proton's rest frame, the background photons are blue-shifted to enormous energies because the proton is moving at nearly the speed of light relative to the background. For a proton with energy above approximately 5 times 10 to the 19th electron volts in the laboratory frame, a head-on collision with a background photon provides enough center of mass energy to produce a pion, a particle consisting of a quark and an antiquark. The proton-photon interaction produces a pion and a slightly lower energy proton, and the pion carries away some of the proton's energy. The energy loss per interaction is modest. A proton loses about 20% of its energy per pion-producing collision. But the mean free path between collisions, at this threshold energy, is approximately 6 megaparsecs, about 20 million light-years. Over a propagation distance of 100 megaparsecs, 300 million light-years, protons starting above the threshold energy will undergo many pion-producing collisions and be degraded in energy significantly below the threshold. Over longer distances, the degradation continues. The prediction is therefore that ultra-high energy cosmic rays observed at Earth with energies above the GZK threshold must originate from within approximately 100 megaparsecs, roughly 300 million light-years. Any proton starting above the threshold from a more distant source will have its energy degraded below the threshold before it arrives. This prediction implies a sharp suppression in the observed flux of cosmic rays above the threshold energy. Below the threshold, cosmic rays can arrive from distant sources throughout the observable universe. Above the threshold, only sources within approximately 100 megaparsecs can contribute. The flux should drop sharply at the threshold. This is the GZK cutoff, a wall at the edge of the observable cosmic ray energy spectrum, not because nothing can accelerate particles to higher energies, but because the universe is opaque to such particles over cosmic distances. The Pierre-Auger Observatory and the telescope array have both found evidence for a suppression in the cosmic ray flux above approximately 40 to 50 eV, broadly consistent with the GZK prediction. The suppression is real, a clear departure from the power law spectrum that describes the cosmic ray flux at lower energies, but the detailed shape of the suppression, and whether it is truly located at the energy predicted by the standard GZK calculation, is sensitive to potential Lorentz invariance violations. If the energy-momentum relation for protons or photons is modified at very high energies, the threshold energy for pion production shifts. A modification that increases the threshold moves the GZK cutoff to higher energies, allowing protons to propagate farther before being degraded. A modification that decreases the threshold moves the cutoff to lower energies. The observed position of the flux suppression has been used to constrain such modifications. The constraints place upper limits on Lorentz invariance violation parameters that are competitive with the best constraints from other methods. They are not the most powerful available for all types of Lorentz invariance violation, but they probe a different physical process and a different energy range than gamma-ray burst observations, providing independent and complementary information. The GZK cutoff, 58 years after its prediction, has become not merely a confirmation of standard particle physics applied to cosmological distances, but a precision test of whether that standard physics holds unchanged at energies where Planck scale corrections might be expected to appear. The wall at the edge of energy is not just a limit on where cosmic rays can come from. It is a probe of whether the physics that creates that limit is exactly the physics that Einstein and his successors wrote down, or whether it is something slightly different. Something with a structure at the deepest level that the equations of special relativity, however confirmed, were never built to describe. Pulsars are neutron stars, the collapsed remnants of massive stars that ended their lives in supernova explosions, that emit beams of radio waves and other electromagnetic radiation from their magnetic poles. Because the magnetic poles are typically misaligned with the rotation axis, the beams sweep across the sky as the neutron star rotates, much as a lighthouse beam sweeps across the sea. Observers in the beam's path detect a pulse of radio emission with each rotation. The most rapidly rotating pulsars, the millisecond pulsars, rotate hundreds of times per second, and their rotational stability is extraordinary. A millisecond pulsar can maintain its rotation rate with a fractional stability of 1 part in 10 to the 19th or better over timescales of years, a stability comparable to or exceeding the best atomic clocks built on Earth. Nature, in creating millisecond pulsars, has produced some of the most precise natural clocks in the universe. This precision is exploited in pulsar timing experiments, which measure the arrival times of pulsar pulses at radio telescopes with the precision required to detect deviations from the expected pulse arrival times at the level of nanoseconds or even sub-nanoseconds. Pulsar timing has been used to test general relativity in the strong field regime, specifically in binary pulsars, where two neutron stars orbit each other at high velocities and in strong gravitational fields, producing gravitational wave emission that causes the orbit to decay in exact agreement with general relativistic predictions. This work earned Russell Hulse and Joseph Taylor the Nobel Prize in Physics in 1993. More recently, pulsar timing arrays, networks of precisely monitored millisecond pulsars distributed across the sky, have been used to search for gravitational wave backgrounds, with evidence for such a background announced in 2023 by multiple international collaborations. For the question of whether the speed of light is energy-dependent, pulsar timing provides a specific and sensitive test. Pulsars emit radiation broadly across the radio spectrum. A single pulse contains emission at many frequencies simultaneously. If the speed of light is frequency-dependent, if radio waves at different frequencies propagate at slightly different speeds, then the arrival time of a pulse at different frequencies will differ, with lower frequency components arriving later than higher frequency components. This is exactly what is observed, and it is completely expected. The ionized interstellar medium, the diffuse plasma of electrons and protons between stars, disperses radio waves in a well-understood way, causing lower frequency waves to travel more slowly. The dispersive delay at any radio frequency is proportional to the integrated electron column density along the line of sight known as the dispersion measure, and it scales as the inverse square of the radio frequency. After accounting for the known interstellar dispersion, which is measured independently for each pulsar and removed from the timing data, any remaining frequency-dependent arrival time differences would constitute evidence for some additional energy-dependent propagation effect beyond standard electrodynamics. This is the signal being sought in pulsar timing tests of the hidden limit. The challenge is that the interstellar dispersion correction is not perfect. The electron density along the line of sight varies in time as the pulsar, the interstellar medium, and Earth all move, and the dispersion measure must be measured and corrected simultaneously with the timing analysis. Residuals in the dispersion correction can masquerade as or conceal any additional frequency-dependent effect. Despite these challenges, pulsar timing has placed competitive constraints on energy-dependent photon propagation. Analysis of timing data from multiple millisecond pulsars, particularly those observed by the Parkes Pulsar Timing Array in Australia, the European Pulsar Timing Array, and the North American Nanohertz Observatory for Gravitational Waves, has placed upper limits on any frequency-dependent arrival time differences beyond standard dispersion at levels competitive with or better than some gamma-ray burst constraints, though probing a different, much lower energy regime of photon propagation. The square-kilometre array, currently under construction in Australia and South Africa, will transform the sensitivity of pulsar timing observations. The SKA will detect radio emission from pulsars with far greater signal-to-noise ratio than any existing telescope, enabling timing precision at the level of tens of nanoseconds for the best pulsars and revealing thousands of new pulsars beyond those currently known. The improved sensitivity will substantially sharpen the constraints on frequency-dependent propagation from pulsar timing, providing constraints that complement those from gamma-ray burst observations at high energies. When the SKA reaches full operation, expected in the early 2030s, it will be one of the most powerful instruments available for the search for the hidden limit, not by looking at the universe's most violent explosions, but by listening to the most precise natural clocks in existence for the faintest possible whisper of inconsistency in the arrival of light. Gamma-ray bursts were discovered accidentally in the late 1960s by the Vela satellites, a series of spacecraft launched by the United States to monitor compliance with the Partial Nuclear Test Ban Treaty of 1963. The treaty prohibited nuclear weapons tests in the atmosphere, in space and underwater, and the Vela satellites were designed to detect the gamma-ray emission characteristic of nuclear detonations. What they found, beginning in 1967 and announced publicly in 1973, was not nuclear tests but something far more extraordinary. Brief, intense flashes of gamma-ray emission arriving from random directions in the sky, from sources evidently far beyond Earth and its vicinity. The origin, energy scale, and physical mechanism of gamma-ray bursts would remain contested for decades, with some astronomers arguing they were relatively nearby phenomena within the Milky Way, and others arguing they were at cosmological distances. The question was not definitively settled until 1997, when the Italian-Dutch Beppo-SX satellite detected an X-ray afterglow from a gamma-ray burst and enabled optical identification of the host galaxy at a redshift, placing it at a distance of several billion light-years. With their cosmological distances established, the extraordinary nature of gamma-ray bursts became fully apparent. A typical long gamma-ray burst, the more energetic of the two main classes, releases approximately 10 to the 44th joules of electromagnetic energy in a period of seconds to minutes. This is comparable to the total electromagnetic energy output of the Sun over its entire 10 billion year lifetime. The most energetic gamma-ray bursts exceed this by orders of magnitude. The energy comes from the gravitational collapse of the core of a massive rotating star, which produces a rapidly rotating black hole, and an accretion disk whose magnetic field launches a relativistic jet of plasma along the rotation axis. The jet, moving at velocities approaching 0.9999 of the speed of light, collides with itself and with surrounding material in a series of shocks that convert the jet's kinetic energy into gamma-ray emission with extraordinary efficiency. For tests of the speed of light, gamma-ray bursts have properties that make them uniquely suited as observational probes. They emit radiation across an enormous range of energies simultaneously. A single burst may produce detectable emission from soft X-rays at a few kilo-electron volts to multi-GeV gamma rays spanning 3 to 4 orders of magnitude in photon energy. They are located at cosmological distances. The most distant detected gamma-ray bursts occurred when the universe was less than 1 billion years old, at distances exceeding 10 billion light-years, providing propagation paths over which even tiny energy-dependent speed differences accumulate into potentially measurable time delays. And the initial emission of a gamma-ray burst is extremely brief. Some bursts show variability on millisecond timescales, providing a well-defined start time against which the arrival of photons at different energies can be measured. The physics argument for why gamma-ray bursts are the ideal probe is straightforward. If 2 photons are emitted simultaneously from the same source, one with energy E1 and one with energy E2, and if the speed of light is energy-dependent in the way predicted by linear Lorentz invariance violation, the higher energy photon will travel at a speed c times 1 minus some small correction proportional to its energy divided by the Planck energy. Over a propagation distance L, the 2 photons will develop a separation in arrival time proportional to the difference in their energies, to the propagation distance, and to the inverse of the Planck energy. For photons with energies differing by 1 giga-electron-volt, emitted from a burst 10 billion light-years away, the predicted time delay is on the order of several tenths of a second, a delay easily measurable with modern gamma-ray detectors. The Fermi Gamma-Ray Space Telescope, launched in June 2008, was specifically designed with sensitivity and energy range suited to these tests. Its large-area telescope detects photons from approximately 20 mega-electron-volts to more than 300 giga-electron-volts, a range of more than 4 orders of magnitude in energy, with timing precision of better than 1 microsecond. Its gamma-ray burst monitor detects lower energy emission from 8 kilo-electron-volts to 40 mega-electron-volts, bridging the gap to the large-area telescope energy range. Together, these instruments span 6 orders of magnitude in photon energy, providing the broadest spectral coverage of any gamma-ray burst instrument in history. In its first several years of operation, Fermi detected dozens of gamma-ray bursts bright enough to measure the arrival times of photons at different energies with statistical precision sufficient to constrain Lorentz invariance violation parameters. The results represent the most stringent constraints ever placed on the energy dependence of the speed of light for photons propagating over cosmological distances, and one specific result, from a burst detected less than a year after launch, was not quite what anyone in the field had anticipated. On May 10, 2009, the Fermi Gamma-Ray Space Telescope was pointed at a region of sky in the constellation Carina, when its gamma-ray burst monitor triggered on a flash of gamma-ray emission. The monitor detected the onset of a short gamma-ray burst, an event lasting less than 2 seconds, and immediately relayed the trigger to the Large Area Telescope, which began recording higher energy photons from the source. The burst, designated GRB 090510 in the standard notation encoding the detection date, would turn out to be one of the most scientifically important gamma-ray bursts ever observed. The burst was at a redshift of 0.903, placing it at a distance of approximately 7.3 billion light-years. This is a substantial fraction of the observable universe. The light that produced this burst was emitted when the universe was less than half its current age. More significantly for the hidden limit question, the burst was extremely hard spectrally. It produced an exceptionally large number of high-energy photons, and the Large Area Telescope detected it over an energy range extending to multi-GeV energies. Among the photons detected was a single photon with energy of approximately 31 GeV. At the time of detection, one of the highest energy photons ever associated with a gamma-ray burst by any instrument. The analysis of this 31 giga-electron-volt photon in the context of Lorentz invariance violation was straightforward in principle. The photon arrived at the Fermi spacecraft approximately 0.829 seconds after the onset of the burst as detected by the gamma-ray burst monitor. If high-energy photons travel slightly more slowly than low-energy photons, as predicted by the most natural version of linear Lorentz invariance violation, then the 31 giga-electron-volt photon should arrive significantly after the lower-energy photons that form the main burst emission. An arrival delay of 0.829 seconds might seem consistent with this prediction. The Fermi collaboration, in a detailed analysis published in the journal Nature in 2009, concluded otherwise. The key insight in the analysis is that the 0.829 second delay relative to the burst onset does not necessarily imply a propagation delay of 0.829 seconds. The observed delay must be compared to the expected intrinsic delay, the time difference that would exist between the emission of the low-energy burst and the emission of the 31 giga-electron-volt photon, even if there were no propagation delay. Gamma-ray burst emission is complex, and there is no reason to assume that all photon energies are emitted at precisely the same moment. The Fermi collaboration argued, based on the spectral and temporal evolution of the burst, that the 31 giga-electron-volt photon was likely emitted at approximately the same time as the main burst emission, or possibly somewhat later, meaning that the 0.829 second arrival delay provides an upper limit on the propagation delay, not a measurement of it. Using this upper limit and the 7.3 billion light-year propagation distance, the Fermi collaboration calculated the corresponding upper limit on the energy-dependent speed coefficient for linear Lorentz invariance violation. The result was remarkable. The upper limit exceeded the Planck energy by a factor of approximately 1.2. In other words, for linear Lorentz invariance violation in the subliminal direction, high-energy photons slower than low-energy photons, the scale at which the violation would become order unity must be greater than 1.2 times the Planck energy. Since physics at energies greater than the Planck energy is not currently described by any consistent theory, this result effectively rules out linear subluminal Lorentz invariance violation for photons. The result was widely interpreted as a major constraint on quantum gravity models. Models of loop quantum gravity that predicted linear subluminal Lorentz invariance violation at the Planck scale were ruled out by a single photon from a single burst. The sensitivity achieved by Fermi's detection of a 31 giga-electron-volt photon from a source 7.3 billion light-years away surpassed the sensitivity achievable by any conceivable laboratory experiment by an enormous margin. Nature provided the baseline, 7.3 billion light-years, that physics needs but cannot build. What the result does not rule out is Lorentz invariance violation in the superluminal direction, high-energy photons traveling faster than low-energy photons, or quadratic Lorentz invariance violation, in which the speed modification scales as the square of the energy rather than the first power, and is therefore suppressed by the square of the Planck energy rather than its first power. These alternatives remain unconstrained at the Planck scale by current observations. They require either the opposite sign of the time delay or a level of precision in measuring small time delays that exceeds what current observations can achieve. The search for these alternatives drives the observational program that continues beyond GRB 090510, and the instruments being built today are designed with precisely this remaining parameter space in mind. The phrase quantum gravity covers a collection of theoretical frameworks rather than a single confirmed theory. Quantum gravity is the not yet achieved unification of general relativity, which describes gravity and the large-scale structure of space-time, with quantum mechanics, which describes the behavior of matter and energy at the atomic and subatomic scale. The two theories are individually the most precisely confirmed theories in the history of physics. They are also mutually inconsistent. Applied to the same physical situation, a region of space small enough for quantum effects on the gravitational field to be significant, they produce predictions that cannot simultaneously be correct. General relativity describes a smooth, continuous space-time. Quantum mechanics implies fluctuating, discrete structures. Something must give. The theory that resolves this inconsistency is quantum gravity, and it does not yet exist in a complete confirmed form. What does exist is a collection of candidate frameworks, each making different assumptions about how the inconsistency is resolved, and each predicting different consequences for observable physics. The common feature relevant to the speed of light is that every serious framework for quantum gravity predicts some departure from the smooth, continuous space-time geometry of general relativity at the Planck scale. The smooth geometry is an approximation, excellent at all scales currently accessible to experiment, but modified in some way at the scale where quantum and gravitational effects become simultaneously important. And since the speed of light is a property of space-time geometry, any modification of the geometry at the Planck scale is potentially a modification of c at Planck scale energies. Loop quantum gravity is currently one of the two most developed candidate frameworks alongside string theory. It takes general relativity as its starting point and applies the techniques of quantum mechanics directly to the geometric degrees of freedom of spacetime, the curvature, the distances, the volumes. The result is a discrete structure. In loop quantum gravity, the area of any physical surface cannot take arbitrary continuous values. It takes values in a specific discrete spectrum with a minimum non-zero area on the order of the Planck area, approximately 10 to the negative 70th square meters. Space is granular at the Planck scale, composed of elementary units of area and volume whose quantum states define the geometry. The smooth manifold of general relativity emerges from this granular structure as a macroscopic approximation, valid when averaged over many elementary units, in the same way that the smooth surface of water emerges as an approximation when averaged over many water molecules. For photon propagation, this granular structure predicts energy-dependent modifications to the speed of light through the mechanism described in earlier sections. Higher energy photons have shorter wavelengths and interact more strongly with the Planck scale granularity, accumulating slightly more delay per unit distance than lower energy photons. The predicted modification to the speed is linear in the ratio of the photon energy to the Planck energy, with a coefficient that depends on the detailed structure of the loop quantum gravity model. Some versions of the calculation predict that the coefficient is of order 1, meaning the effect is exactly at the Planck suppressed level, while others predict that it's significantly smaller. The diversity of predictions within loop quantum gravity reflects the fact that the theory is not yet complete, and the specific calculation connecting the granular structure to the photon propagation speed involves approximations whose validity is debated. String theory approaches the problem from a radically different direction. Its fundamental objects are one-dimensional strings, objects extended in one spatial dimension whose different vibrational modes correspond to different elementary particles. The photon in string theory is one of the massless modes of the open string. Gravity, and the graviton, arises from closed string modes. Spacetime itself is not a fixed background on which strings move, but is in some sense generated by the collective behavior of the strings. String theory requires extra spatial dimensions, 10-dimensional spacetime in the most common formulations, with the extra 6 dimensions compactified at scales far smaller than this Planck length to explain why they are not observed. For Lorentz invariance and the speed of light, string theory is more subtle than loop quantum gravity. In the simplest versions, string theory is exactly Lorentz invariant at all energies and predicts no energy-dependent modification to the photon speed. But in realistic compactifications, where the extra dimensions are curled up in specific geometric shapes, the effective 4-dimensional theory can break the exact Lorentz invariance of the full 10-dimensional theory, producing modifications that depend on the specific compactification. The landscape of possible string theory vacua, estimated at 10 to the 500th distinct compactifications, means that string theory does not make a unique, definite prediction for the magnitude of any Lorentz invariance violation. It can accommodate a wide range of possibilities, from no modification whatsoever to modification significantly larger than Planck scale suppression. This makes string theory less testable by Lorentz invariance violation searches than loop quantum gravity, but not entirely untestable. Any detected modification would constrain which region of the string landscape describes our universe. The Planck scale is not a place or an energy that any experiment has ever reached. It is the scale at which current physics explicitly breaks down, the point where the equations of both general relativity and quantum mechanics produce nonsense when applied simultaneously, and where a new theoretical framework is required to make sense of what happens. It is defined not by any observation but by the combination of 3 fundamental constants: the speed of light c, the gravitational constant g, and the reduced Planck constant h bar. From these 3 constants, unique values of length, time, mass, energy, and temperature can be constructed, and these values define the Planck scale. The Planck length is approximately 1.616 times 10 to the negative 35th meters. To develop intuition for how small this is, consider the following sequence of scales. The diameter of a hydrogen atom is approximately 10 to the negative 10 meters. The diameter of a proton is approximately 10 to the negative 15 meters, 5 orders of magnitude smaller than the atom. The diameter of a quark, if quarks have any size at all, is smaller than 10 to the negative 18 meters, 3 more orders of magnitude smaller. The Planck length is 10 to the negative 35th meters, 17 orders of magnitude smaller than a quark, or 20 orders of magnitude smaller than a proton. If a proton were magnified to the size of the observable universe, approximately 10 to the 26th meters across, the Planck length in that magnified view would be approximately 1 centimeter. 1 centimeter in a proton scale to the size of the observable universe. This is how deep the Planck scale is beneath anything that has ever been directly probed. The Planck time is the time required for light to travel 1 Planck length, approximately 5.4 times 10 to the negative 44th seconds. The shortest time intervals ever measured by any physical technique are on the order of 10 to the negative 22nd seconds, attoseconds, used in ultra-fast laser spectroscopy of atomic dynamics. The Planck time is 22 orders of magnitude shorter than an attosecond. Processes occurring at the Planck timescale cannot be resolved by any conceivable measurement technology based on current physical principles. The Planck energy is approximately 1.22 times 10 to the 19th giga-electron volts, about 1.22 times 10 to the 28th electron volts. The highest energies produced by the Large Hadron Collider are approximately 6.5 times 10 to the 3 giga-electron volts per beam. The ratio of the LHC energy to the Planck energy is approximately 10 to the negative 15, 10 to the negative 15th. The Planck energy is 15 orders of magnitude beyond the highest energy any human technology has ever produced. At the Planck scale, the physics of spacetime is expected to be qualitatively different from anything described by current theories, for a fundamental reason that follows directly from combining general relativity and quantum mechanics. General relativity says that energy warps spacetime geometry. Quantum mechanics says that any localized region of space contains quantum fluctuations in energy of magnitude inversely proportional to the size of the region. At the Planck length, the quantum fluctuations in energy in a Planck volume region are comparable to the Planck energy, the energy whose gravitational effect would warp the surrounding spacetime by an amount comparable to the syn spacetime's own size. In other words, at the Planck scale, the quantum fluctuations of the gravitational field of spacetime geometry itself are order unity. The geometry is not slightly perturbed from flat. It fluctuates wildly, creating and destroying structures at the Planck length and the Planck time. The smooth geometry of general relativity is not an approximation here. It is inapplicable. This breakdown of the smooth geometry is not a failure of physics. It is a signal that physics has reached the boundary of its current descriptions and that something new must take over. Every previous boundary of this kind, the failure of Newtonian mechanics at high velocities, the failure of classical physics at atomic scales, has led to a deeper and more complete description. The boundary at the Planck scale is expected to lead to quantum gravity, the description of spacetime as a quantum system, subject to the same superposition and uncertainty that govern electrons and photons. The nature of this quantum spacetime, whether it is discrete like loop, quantum gravity suggests, or continuous but higher dimensional like string theory suggests, or something entirely different, is the central open question in theoretical physics. What is almost universally agreed upon is that whatever happens at the Planck scale, it reflects upward to observable scales through the propagation of high-energy particles. The speed of light, a property of space-time geometry, cannot be isolated from the geometry's behavior at its deepest level. If the geometry is fundamentally different at the Planck scale from the smooth manifold that special relativity describes, the speed of light may be subtly different at energies approaching the Planck scale from the constant value it takes at accessible energies. The Planck scale is where the hidden limit lives, if it lives anywhere. Loop quantum gravity begins with a deceptively simple premise. Take general relativity seriously as a theory of geometry and apply the standard techniques of quantum mechanics to its geometric degrees of freedom. General relativity describes gravity as the curvature of a four-dimensional spacetime manifold. The equations of general relativity determine how the curvature responds to the distribution of matter and energy, and how matter and energy move through the curved spacetime. In loop quantum gravity, these geometric degrees of freedom, the curvature, the metric, the connection that determines how vectors are parallel transported through spacetime, are promoted from classical fields to quantum operators, subject to the Heisenberg uncertainty principle and capable of existing in quantum superpositions. The mathematical implementation of this program is technically demanding and involves the use of specific variables, loop variables, and spin network states that simplify the quantum mechanics of spacetime geometry considerably relative to earlier attempts at quantizing gravity. The result is a theory in which the quantum states of spatial geometry are described by spin networks, abstract graphs whose nodes represent elementary volumes and whose edges represent elementary areas. Each edge carries a quantum number, an integer or half-integer, that determines the area of the elementary surface it represents according to a specific formula involving the Planck length and the quantum number. The minimum non-zero area corresponds to a quantum number of 1/2 and has a value of approximately 5.17 times the Planck area, a tiny but finite minimum size for any geometric surface. Space in loop quantum gravity is granular at the Planck scale. The emergence of a minimum area in loop quantum gravity is not an assumption introduced by hand, it is a calculation result, a consequence of applying the commutation relations of quantum mechanics to the geometric variables of general relativity. The quantization of geometry is analogous to the quantization of energy levels in an atom. Just as an electron in a hydrogen atom can only have discrete quantized energy values, the area of any surface in quantum spacetime can only have discrete quantized values. The discreteness is a fundamental prediction of the theory, not a free parameter that can be tuned. For photon propagation, this granular spacetime structure introduces energy-dependent modifications to the speed of light through a mechanism that can be understood intuitively. A photon propagating through spacetime interacts with the quantum geometry through which it passes. At energies far below the Planck energy, all energies accessible to current experiments, the photon's wavelength is much larger than the Planck length, and the granularity of spacetime is far too fine to be resolved. The photon essentially sees a smooth background and propagates at c. As the photon energy increases toward the Planck energy, its wavelength approaches the Planck length, and it begins to resolve the granular structure. The interaction with the Planck scale granularity affects the propagation, in the same way that a sound wave propagating through a crystal lattice is affected by the lattice structure when the sound wavelength approaches the lattice spacing. The propagation speed becomes energy-dependent when the wavelength approaches the structure scale. The specific form of the energy-dependent speed modification in loop quantum gravity has been calculated by several groups using different approximation schemes, and the results are not fully consistent with each other, reflecting the fact that the relevant calculations are technically difficult and the theory is not yet complete enough to make unique predictions. The consensus prediction is that the speed modification is of order the photon energy divided by the Planck energy, linear Lorentz invariance violation, but the precise coefficient and sign of the modification are not uniquely determined. Some calculations predict that higher energy photons travel slightly more slowly than lower energy photons, subluminal violation, while others predict the opposite. The GRB 090510 constraint has effectively ruled out subluminal linear Lorentz invariance violation at the Planck scale, but superluminal linear violation and all forms of quadratic violation remain unconstrained at the Planck energy level. Loop quantum gravity has motivated a specific and important prediction beyond just Lorentz invariance violation in photon propagation. It predicts that the discrete structure of spacetime produces a characteristic correction to the standard dispersion relation, the equation relating the energy and momentum of a photon that distinguishes it from other possible corrections. In principle, observations of many photons at different energies from many gamma-ray bursts at different distances, with sufficient statistical precision, could determine not just whether a propagation time delay exists, but whether its energy and distance dependence matches the specific functional form predicted by loop quantum gravity. Such a measurement would represent a true precision test of quantum gravity, not just a constraint on whether it exists, but a determination of which version of it is correct. This is the long-term scientific goal that motivates the current observational program. String theory is the other leading contender for a theory of quantum gravity, and it approaches the problem from a direction almost orthogonal to loop quantum gravity. Where loop quantum gravity takes general relativity as its starting point and quantizes its geometric content, string theory begins with quantum mechanics, specifically the quantum mechanics of one-dimensional extended objects called strings, and finds that gravity emerges inevitably from the theory's internal consistency requirements. The photon in string theory is one mode of vibration of an open string. The graviton, the quantum of the gravitational field, is one mode of vibration of a closed string. The different fundamental particles correspond to different modes of vibration of the same fundamental string, and the different forces arise from different types of string interactions. String theory requires, as a mathematical necessity, that space-time has more dimensions than the four we observe. The original formulations required 26 space-time dimensions for bosonic strings. Modern superstring theories require 10 space-time dimensions, 1 time and 9 spatial dimensions. The 6 extra spatial dimensions must be curled up at scales far smaller than any that have ever been probed experimentally, explaining why they are not observed directly. The specific geometric shape in which the extra dimensions are compactified, the Calabi-Yau manifold or other compactification geometry, determines the physics of the four-dimensional effective theory seen by low-energy observers. Different compactifications produce different effective theories with different particle content, different force strengths, and potentially different levels of Lorentz invariance violation. The implications for the speed of light in string theory are more complex and less definitive than in loop quantum gravity. In the simplest version of string theory, formulated on a flat 10-dimensional background spacetime, Lorentz invariance is exact. The string theory is invariant under the full 10-dimensional Lorentz group, and the 4-dimensional effective theory inherits this invariance for the 4 dimensions we observe. In this simple version, there is no energy-dependent modification to the speed of light, and the hidden limit does not exist within string theory. But this simple version is not the version that describes the observed universe. The observed universe has a specific low-energy particle content, specific force strengths, and specifically 3 large spatial dimensions. Reproducing this content from string theory requires a specific compactification of the 6 extra dimensions, and the specific compactification may break some of the 10-dimensional Lorentz symmetry when projected onto the 4-dimensional effective theory. The symmetry breaking arises because the compact dimensions have specific geometric shapes with specific symmetries, and these symmetries may not align perfectly with the Lorentz symmetry of the 4-dimensional effective theory. Different compactifications produce different patterns of symmetry breaking and different magnitudes of Lorentz invariance violation. The problem is that string theory does not uniquely predict which compactification describes our universe. The landscape of consistent string theory compactifications is estimated to contain approximately 10 to the 500th or perhaps 10 to the 1000th distinct solutions, each corresponding to a different possible universe with different physical constants and particle content. Without knowing which solution describes our universe, and without a dynamical mechanism within string theory that selects one solution over others, string theory cannot make a definitive quantitative prediction for the magnitude of Lorentz invariance violation in the 4-dimensional effective theory of our universe. This is one of the deepest challenges facing string theory as a scientific theory. A theory that makes no definite quantitative predictions cannot be tested. String theorists have responded to this challenge in several ways. Some argue that anthropic reasoning, the observation that intelligent observers can only exist in universes with certain ranges of physical constants, selects a specific region of the landscape. Others argue that dynamical mechanisms will eventually be found that select a unique vacuum. Still others argue that string theory makes definite predictions for other observable, such as the particle content at the Large Hadron Collider, or the spectrum of gravitational waves from the early universe, even if it does not make definite predictions for Lorentz invariance violation specifically. From the perspective of the observational search for the hidden limit, the string theory situation means that any detected Lorentz invariance violation would constrain which region of the string theory landscape could describe our universe, rather than confirming or ruling out string theory as a whole. A detected effect at the Planck scale would rule out the large portion of the landscape where the effective 4-dimensional theory preserves exact Lorentz invariance. A null result would constrain the effect to be below the observed threshold, ruling out portions of the landscape where violations larger than the threshold occur. In either case, the observations would provide information about which kind of string theory vacuum we inhabit, information that cannot currently be obtained in any other way. One of the most powerful conceptual tools for thinking about the hidden limit without committing to any specific theory of quantum gravity is the refractive universe picture. In this framework, the vacuum of space is treated as an the question of whether the speed of light is energy dependent is recast as the question of whether this medium is an energy dependent refractive index. The refractive universe picture does not explain why the vacuum might be refractive. It simply parameterizes the possibility in a way that makes it directly testable and that applies equally to any underlying theory that predicts the effect. The analogy with ordinary optics is instructive. When light enters a piece of glass, it slows down. The ratio of the speed of light in vacuum to its speed in the glass is the refractive index of the glass, which for typical optical glass is approximately 1.5. This slowing down is not mysterious. It arises from the interaction of the light with the electrons in the glass, which absorb and re-emit the electromagnetic wave in a way that effectively reduces its propagation speed. In most optical materials, the refractive index is not constant across all wavelengths of light. It varies with wavelength scale. It is higher for shorter wavelengths, higher frequency, higher energy light, than for longer wavelengths. This wavelength dependence of the refractive index is called dispersion, and it is responsible for the familiar splitting of white light by a prism. Different wavelengths are refracted by different amounts at the glass-air interface because they travel at different speeds within the glass. The refractive universe picture asks whether the vacuum has a similar dispersion, whether it has an effective refractive index that varies with photon energy, not at the energies of visible light, where the vacuum is measured to be indistinguishable from unity, but at energies approaching the Planck energy. The predicted effect is extraordinarily small compared to glass dispersion. The ratio of the energy of any detectable photon to the Planck energy is at most 10 to the negative 8 or so for the highest energy photons ever detected. The refractive index of the vacuum at any accessible energy deviates from 1 by at most this tiny amount. But over propagation distances of billions of light years, even this tiny deviation accumulates into a time delay between photons of different energies that can in principle be detected. The refractive universe framework is usually expressed as a modification of the dispersion relation, the equation relating a photon's energy E to its momentum p and the speed of light. In standard physics, for a massless photon, E equals pc exactly. In the refractive universe picture, this relation is modified by terms that depend on powers of E divided by the Planck energy. The first-order modification gives E equals pc times the square root of 1 plus some coefficient times E divided by the Planck energy, a modification that is linear in energy divided by the Planck energy, and produces a speed that departs from c at first order in this ratio. The second-order modification replaces the linear term with a quadratic one, giving a speed that departs from c at second order in the ratio of the photon energy to the Planck energy. The first-order effect is what GRB 090510 constrained. The second-order effect is what future observations aim to reach. The power of the refractive universe picture lies precisely in its theory independence. It does not matter whether the underlying physics is loop quantum gravity, string theory, causal set theory, or something not yet imagined. Any theory that predicts an energy-dependent modification to the photon dispersion relation can be expressed in terms of the refractive universe parameters, the coefficients of the first-order and second-order terms, and constrained by the same astrophysical observations. The observations constrain the parameters directly and apply to all theories that predict modifications within the parameterized range. This is the approach adopted by the observational community in practice. Rather than testing specific theoretical models one at a time, they test the refractive universe parameter space comprehensively and note which theories are consistent with the resulting constraints. The current observational constraints from gamma-ray bursts, cosmic rays, and pulsar timing rule out the refractive universe with a first-order coefficient of order 1, the simplest prediction of the most optimistic quantum gravity models. They have begun to probe the first-order parameter space below unity, placing limits that constrain even theories in which the coefficient is somewhat smaller than the Planck energy suppressed level. The second-order parameter space, corresponding to quadratic Lorentz invariance violation, remains largely open at the Planck scale and represents the primary target for the next generation of observational instruments. The possibility that the speed of light might not be a true constant, that c might have varied in the past, might vary in the future, or might vary depending on circumstances, is not a new speculation. It is an idea with a serious theoretical history that predates the specific quantum gravity motivations discussed in this video, and it represents a distinct thread in the broader inquiry into the constancy of C. Understanding variable speed of light theories and what distinguishes them from the quantum gravity picture is important for appreciating the full landscape of physics that intersects with the speed of light question. The cosmological horizon problem is the primary motivation for variable speed of light theories. The cosmic microwave background, the afterglow radiation of the early universe detected in every direction in the sky, has a temperature that is uniform to better than 1 part in 100,000 across the entire sky. In standard cosmology, different regions of the sky, separated by more than about 2 degrees, were not in causal contact with each other before the microwave background was emitted. The universe had not expanded enough for a light signal to travel between them. Yet these causally disconnected regions have the same temperature to extraordinary precision. Without some mechanism to establish this uniformity, the uniformity is extraordinarily improbable, a problem that has been called the horizon problem. The standard resolution of the horizon problem is cosmic inflation, a period of extremely rapid exponential expansion in the very early universe, during which a small region, already in thermal equilibrium but was expanded enormously, producing a large region in which everything is nearly identical because it all descended from the same small equilibrated patch. Inflation has become a cornerstone of the standard cosmological model because it solves the horizon problem and also the flatness problem, and because its prediction of specific patterns of primordial density fluctuations matches the observed patterns in the cosmic microwave background with extraordinary precision. But in the 1990s, 2 independent groups von João Magejo and Andreas Albrecht, and separately John Moffat, proposed that the horizon problem could be solved without inflation if the speed of light was much larger in the early universe than it is today. If C was enormously higher in the first moments after the Big Bang, then even widely separated regions could have been in causal contact, establishing thermal equilibrium before the microwave background was emitted. As the universe cooled and expanded, C decreased to its current value. The uniformity of the microwave background reflects the causal contact established when C was large, not anything that happened after it settled to its current value. Variable speed of light theories face several theoretical difficulties. Changing C is not as simple as it might appear, because C appears in so many fundamental equations that changing it alters many other predictions simultaneously. The fine structure constant, the dimensionless number that characterizes the strength of the electromagnetic interaction, depends on the speed of light, the elementary charge, and the Planck constant. If C varies, the fine structure constant varies, and observations of atomic spectra from distant quasars, whose light was emitted when the universe was young, place tight constraints on any variation of the fine structure constant over the cosmic history. These observations are consistent with a constant or extremely slowly varying fine structure constant which constrains how much C could have varied over the history of the universe. The conceptual connection between variable speed of light theories and the quantum gravity picture of the hidden limit is important to understand clearly because they are different phenomena. Variable speed of light theories propose that C has evolved over cosmic time, that the value of C depends on the age or the state of the universe. The quantum gravity picture proposes that C is energy dependent at any given time, that a high-energy photon and a low-energy photon emitted simultaneously from the same source propagate at slightly different speeds. These are distinct physical claims with different observational signatures. The cosmological variation in C, if it occurred, would affect all photons equally regardless of energy. The variation is a property of the epoch, not the photon. The quantum gravity energy dependence is a property of the photon energy, detectable as an energy-dependent time delay between photons of different energies from the same source. Both ideas question the perfect constancy of C, and both take seriously the possibility that the constant Einstein placed at the foundation of special relativity may have a richer structure than the equations of 1905 imply. Neither has been confirmed observationally. Both represent serious scientific inquiry into the limits of one of physics' most foundational assumptions. Together they illustrate that the question of the constancy of C is not a simple binary, either constant or not constant, but a multidimensional space of possibilities. each with different physical motivation and different observational predictions. The central observational prediction of quantum gravity theories with Lorentz invariance violation is simple enough to state in a single sentence. Two photons of different energies, emitted at the same time from the same distant source, arrive at a detector at different times. The higher energy photon arrives either earlier or later than the lower energy photon, depending on the sign of the Lorentz invariance violation, by an amount proportional to the difference in their energies and to the distance they have travelled. This is the signal being sought in the gamma-ray burst timing analyses that have produced the strongest current constraints on the hidden limit. The challenge in searching for this signal is not instrumentation. Modern gamma-ray telescopes have timing precision far better than the delay predicted by the most optimistic quantum gravity models for typical observed bursts. The challenge is separating the propagation signal from astrophysical noise. The propagation signal looks like a systematic tendency for higher energy photons to arrive consistently earlier or later than lower energy photons, with the time difference scaling with the propagation distance. The noise is everything else that might cause higher energy photons to arrive earlier or later than lower energy photons for reasons unrelated to propagation. Intrinsic time delays in the emission of different energies at the source, spectral evolution of the burst over time, and statistical fluctuations in the photon arrival times from a source with limited total photon count. The intrinsic source delay is the most problematic. Gamma-ray burst emission is complex. Different energy bands brighten and fade at different rates, different spectral components peak at different times, and the relationship between the timing of emission at different energies is not precisely predicted by any current model of the physical mechanism. If high-energy emission is systematically delayed relative to low-energy emission at the source, which some models predict based on the physics of shock acceleration in the burst jet, then a measurement that finds high-energy photons arriving late cannot distinguish between a source delay and a propagation delay without additional information. Several strategies have been developed to address this problem. The most powerful is the distance scaling test. If the measured time delay between high-energy and low-energy photons scales linearly with the distance to the burst, it is almost certainly a propagation effect rather than a source effect, since the source physics should not know how far away the observer is. Implementing this test requires a sample of many bursts at different distances, with measurable high-energy photon delays at each distance, and sufficient statistical precision to detect the linear scaling through the scatter caused by varying source delays. Current Fermi data provide dozens of bursts with measurable energies-dependent time differences, and the analysis of these bursts as an ensemble provides better constraints than any single burst can provide. A complementary strategy uses the information available within a single burst more carefully. Some bursts show rapid, well-defined variability in their light curves, distinct pulses separated by quiet intervals that provide a reference time against which the arrival of high-energy photons can be measured. If a specific pulse in the low-energy light curve has a precise onset time, and a high-energy photon is detected at a specific time relative to this onset, the photon provides a measurement of the propagation delay subject only to the uncertainty in when exactly it was emitted during the pulse. For bursts with clear, sharp variability and detected high-energy photons, this approach can provide stringent constraints from a single burst, GRB 090510 being the prime example. Future progress on the signal versus noise problem requires both improved instrumentation and improved theoretical understanding of burst emission physics. On the instrumentation side, the Cherenkov telescope array will detect substantially more high-energy photons per burst than the Fermi Large Area Telescope, improving the statistical power of time delay measurements for any individual burst. On the theoretical side, advances in numerical simulation of gamma-ray burst jets and their emission mechanisms will improve the predictions for intrinsic source delays, allowing more confident subtraction of source effects from the measured total delay. The photons that travel at different speeds, if they exist, are not a curiosity. They are a message from the Planck scale, encoded in the timing of light that has crossed billions of light-years of quantum spacetime. Detecting the message requires distinguishing it from the noise of astrophysical processes that know nothing about Planck physics and care nothing about the questions of fundamental physics that the observations are designed to answer. This is the essential challenge of observational quantum gravity, and it is being met, imperfectly but progressively, by the growing sensitivity of gamma-ray astronomy, combined with the growing sophistication of the statistical and theoretical methods used to interpret the data. Every burst that is detected, every high-energy photon that is timed, adds one more data point to the answer that physics has been seeking since the idea of a hidden limit was first articulated. Beyond timing, measurements of individual photon arrival times, the hidden limit would produce a second independent observational signature in the spectra of gamma-ray bursts, a systematic distortion of the energy distribution of detected photons that depends on the propagation distance and the energy dependence of the photon speed. This spectral signature provides a complementary test of Lorentz invariance violation that does not require measuring the arrival time of any individual photon, but instead uses the statistical distribution of photon energies detected over the full duration of a burst. The physical mechanism producing the spectral distortion is straightforward. If high-energy photons travel more slowly than low-energy photons, the prediction of subluminal Lorentz invariance violation, then the high-energy portion of a burst's emission falls progressively further behind the low-energy portion as the burst light propagates through space. For nearby bursts, the accumulated delay is small and the high-energy and low-energy photons arrive within a short time of each other. For distant bursts, the delay can become so large that the high-energy photons, which were emitted during the few seconds of the burst itself, arrive minutes, hours, or even days after the low-energy photons. Since gamma-ray detectors monitor sources for a limited time after the burst trigger, typically a few thousand seconds at most, the high-energy photons from very distant bursts might arrive after the detector has moved on to other observations, resulting in no detection of very high-energy photons from that burst. The observational consequence is a correlation between the maximum detected photon energy from a burst and the distance to the burst. Nearby bursts can be detected at all energies up to the maximum energy produced by the source. Distant bursts, if subluminal Lorentz invariance violation is real, would show a systematic deficit of very high-energy photons, not because the source produces fewer of them, but because the detector is not operating long enough to capture the high-energy photons after their longer propagation time. The maximum detected photon energy from a burst would decrease as the burst distance increases, following a specific functional form determined by the magnitude of the Lorentz invariance violation and the energy dependence of the speed modification. Searches for this spectral energy distance correlation have been conducted using catalogues of gamma-ray bursts detected by the Fermi Large Area Telescope and other instruments. The analysis compares the maximum detected photon energy from each burst to the burst's distance, accounting for other factors that influence the maximum detected energy, particularly the intrinsic brightness of the burst, which determines how many high-energy photons are emitted in the first place, and the redshift of the burst, which shifts all photon energies to lower values by a factor of 1 plus the redshift. After accounting for these factors, any remaining correlation between maximum detected energy and distance would be evidence for the spectral distortion caused by energy-dependent propagation. The current results of these analyses are consistent with no detectable spectral distortion at the level of linear Lorentz invariance violation, consistent with the constraints derived from timing measurements of individual high-energy photons. The consistency between the two methods provides additional confidence in the conclusion that linear, subluminal Lorentz invariance violation at the Planck scale is ruled out. But the spectral method has different systematic uncertainties than the timing method. It is less sensitive to the uncertain intrinsic source delay, but more sensitive to the uncertain intrinsic spectrum of the burst. So the two methods provide genuinely independent and complementary constraints, rather than simply repeating the same measurement in a different way. An important subtlety in the spectral analysis is the distinction between the intrinsic high-energy spectrum of the burst and the detected spectrum after propagation effects. If bursts intrinsically produce fewer very high-energy photons than they produce moderate-energy photons, which is always the case since the photon spectrum falls with increasing energy, then distinguishing this intrinsic spectral softening from the distortion caused by Lorentz invariance violation requires careful modelling of the expected intrinsic spectral shape. Advances in understanding gamma-ray burst emission physics, combined with larger statistical samples and better sensitivity instruments, will gradually improve the ability to make this distinction, and thereby improve the sensitivity of the spectral test. The spectral approach to testing the hidden limit represents a different way of asking the same fundamental question. Does the universe treat all photons identically, regardless of energy, Or does it impose an energy tax on the highest energy photons in the form of a slightly reduced propagation speed? The timing test asks whether individual high-energy photons arrive on time. The spectral test asks whether high-energy photons arrive at all. Together, they probe the hidden limit from complementary angles, and their agreement, or eventual disagreement, will be a significant input into the final determination of whether the speed of light has a hidden structure beyond what special relativity reveals. The masslessness of the photon is one of the most precisely established facts in all of physics, both theoretically and experimentally. Theoretically, it is a consequence of gauge symmetry, the mathematical structure of electromagnetism that makes the theory renormalizable, self-consistent, and applicable at arbitrarily short distances. Experimentally, the mass of the photon has been bounded from above by a succession of increasingly sensitive measurements, and the current upper limit is so small that the photon might as well be massless for any practical physical calculation. Yet the question of whether the photon has an exactly zero mass or merely an extremely small but non-zero mass touches on foundational issues in gauge theory and connects in interesting ways to the broader question of the speed of light. The theoretical argument for masslessness is straightforward. Electromagnetism is described by a gauge theory, specifically by a U1 gauge theory, whose gauge field is the electromagnetic potential. The gauge invariance of this theory, the fact that the equations of motion are unchanged by a specific class of transformations of the potential, requires that the gauge field be massless. Adding a mass term for the photon to the Lagrangian of electrodynamics breaks the gauge invariance, producing a theory, called Procur electrodynamics, that is not renormalizable in the same sense as massless electrodynamics, and that predicts qualitatively different behavior of the electromagnetic field at long distances. Specifically, a massive photon theory predicts that the electromagnetic force has a finite range determined by the photon's Compton wavelength, rather than the infinite range of massless electrodynamics. The electromagnetic force between two charges would fall off faster than the inverse square law at distances larger than the Compton wavelength. Measurements of the electromagnetic field over large distances have found no evidence for such a departure from the infinite range inverse square law, providing strong constraints on the photon mass. The most stringent direct constraint comes from measurements of the magnetic field of Jupiter by the Voyager 1 spacecraft, which constrained the photon mass to be less than approximately 8 times 10 to the negative 52nd kilograms. More stringent constraints come from theoretical arguments based on the absence of large-scale electric fields in the cosmos, and from precision measurements of the magnetic vector potential using laboratory circuits. The current best upper limit from cosmic magnetic field considerations places the photon mass below approximately 10 to the negative 54th kilograms, a number so small that it's 38 orders of magnitude less than the mass of the electron. If the photon had a mass at or below this upper limit, what would the consequences be for the speed of light? A massive photon would not travel at exactly c. Its speed would depend on its energy according to the relativistic formula. The velocity equals c times the square root of 1 minus the ratio of the rest mass energy squared to the total energy squared. For photon energies far greater than the rest mass energy, which is the case for every photon that has ever been detected, given the tiny upper limit on the photon mass, the speed is extremely close to c, differing by an amount proportional to the square of the rest mass energy divided by the square of the photon energy. Higher energy photons would travel faster than lower energy photons, approaching c more closely, while lower energy photons would travel at speeds fractionally below c. This energy-dependent speed has the opposite sign from the prediction of subluminal Lorentz invariance violation from loop quantum gravity. Massive photon effects cause high-energy photons to be faster, while subluminal quantum gravity effects cause high-energy photons to be slower. This opposite sign is useful observationally. A measurement that finds high-energy photons arriving before low-energy photons from the same distant burst could in principle be caused by either a non-zero photon mass or by superluminal Lorentz invariance violation. But the two can in principle be distinguished by the functional form of the energy dependence. Photon mass produces a quadratic energy dependence, the delay scales as the inverse square of energy, while linear Lorentz invariance violation produces a linear energy dependence. Current observations from gamma-ray burst timing and from radio pulsar observations have placed constraints on the photon mass that are competitive with laboratory bounds, in some cases exceeding them. The consistency of these astrophysical constraints with the laboratory constraints and the absence of any detected energies-dependent propagation signal attributable to photon mass, confirms that if the photon has mass, it is below the current observational sensitivity. The photon mass question remains open in the sense that the mass is constrained to be below a very small number rather than measured to be exactly zero, but the constraints are tight enough that photon mass effects on light propagation are negligible at all energies currently accessible to astronomy. Special relativity divides the universe of possible motions into three fundamentally different categories, separated by the speed of light. Objects with mass, particles, atoms, planets, spacecraft, travel at speeds below c in any inertial reference frame. Massless particles, photons, gravitons, travel at exactly c. And then there is the third category, objects whose speed exceeds c. In special relativity, this third category is not merely prohibited by practical considerations or by the energy requirements of acceleration. It is a geometrically distinct regime, separated from the first two categories by a barrier that cannot be crossed from either side. The barrier arises from the structure of the Lorentz transformation. Accelerating a massive object from rest requires increasing its energy continuously, and the energy required grows without bound as the speed approaches. The relativistic kinetic energy of a massive object diverges to infinity as its velocity approaches the speed of light. No finite energy, and no matter how large, can accelerate a massive object to c. The speed of light is not a very high speed limit. It is an unreachable limit, like the horizon, always the same distance away no matter how far you travel toward it. On the other side of c, however, the mathematics of special relativity does not immediately break down. A particle that has always been travelling faster than c, a particle that was never on the slow side of the limit and never needed to cross the barrier, is not obviously inconsistent with the mathematical structure of the theory. Such a particle, postulated in the 1960s by physicists George Sudarshan, Alexa Myron-Bilaniuk, and Gerald Feinberg, was given the name tachyon from the Greek word for swift. Unlike ordinary particles, for which mass squared is positive and real, a tachyon has an imaginary mass, a mass squared that is negative. This imaginary mass is not the same as having no mass. It characterizes the specific way in which a tachyon's energy-momentum relation differs from that of an ordinary particle. The energy-velocity relationship for tachyons is the inverse of the relationship for ordinary particles. For a massive particle, kinetic energy increases as speed increases, reaching infinity at c. For a tachyon, energy decreases as speed increases, reaching zero as speed approaches infinity. A tachyon at any finite energy is moving at a speed greater than c, and a tachyon with zero energy is moving at infinite speed. It is everywhere simultaneously. Bringing a tachyon to rest, making it travel at zero speed, would require an infinite amount of energy input from outside, just as accelerating an ordinary massive particle to c would require infinite energy. The tachyon and the massive particle are mirror images of each other. Reflected across the barrier of c, tachyons, if they exist, pose severe problems for causality. A tachyon signal, combined with the relativity of simultaneity and special relativity, can under some circumstances be used to send information to the past, to violate the ordinary temporal ordering of cause and effect. The precise analysis of this causality problem is subtle, and has been debated since tachyons were first proposed. But the consensus view is that free, controllable tachyons would allow the construction of paradoxes inconsistent with a consistent temporal ordering of events. This causality problem is generally taken to rule out tachyons as physical signals capable of carrying information, even if the mathematics of a faster-than-light particle is not inherently inconsistent. Tachyons do appear in physics, but not as literal faster-than-light particles. They appear as mathematical indicators of an unstable vacuum state in quantum field theory. When a quantum field has an imaginary mass parameter in the theory, the field is tachyonic, but this means not that the corresponding particles travel faster than light, but that the vacuum of the theory is at an energy maximum rather than a minimum, and that the system will spontaneously evolve to a lower energy configuration. The most famous example is the Higgs field in the Standard Model before electroweak symmetry breaking. In the symmetric phase of the electroweak theory, the phase that existed when the universe was very hot, the Higgs field has an imaginary mass parameter and is tachyonic in this technical sense. The tachyonic instability drives the Higgs field to its non-zero vacuum expectation value, breaking the electroweak symmetry and giving mass to the Dullian Z bosons. The tachyon here is not a particle that travels faster than light. It is a mathematical signal that the symmetric vacuum is unstable and will spontaneously decay to the broken symmetry vacuum. No experimental evidence for physical tachyons, particles that literally propagate faster than light, has ever been found. The question of whether the universe contains anything on the other side of the speed limit remains open as a logical possibility, but is unsupported by any observation. The hidden limit explored in this video is not a claim about the other side. It's a question about the limit itself, whether C is as sharp and absolute as it appears, or whether the geometry that produces it has a structure at depths not yet explored. The speed of light is the speed limit of the universe. This much is commonly known. But the reason for the limit is understood by far fewer people, and without understanding the reason, the significance of any potential modification to C cannot be properly appreciated. The limit is not about energy. It is not primarily about momentum or inertia, or any of the mechanical concepts that dominate intuitions about fast-moving objects. The deepest reason why nothing can travel faster than light is causality. The requirement that causes precede their effects in time, that information cannot travel from the future to the past, that the sequence of events in the universe has a consistent and unambiguous temporal order. The connection between the speed of light and causality is one of the most profound results of special relativity, and it follows directly from the combination of two features of the theory, the relativity of simultaneity and the geometry of space-time. The relativity of simultaneity says that two events which are simultaneous in one reference frame are not necessarily simultaneous in another frame moving relative to the first. Two events that occur at the same time but the different places in one frame occur at different times in another frame. And which event occurs first depends on the relative velocity and direction of motion. This frame dependence of temporal ordering is deeply counterintuitive to everyday experience, but is a mathematically inevitable consequence of the Lorentz transformation, and has been confirmed experimentally in numerous contexts. Now suppose that a signal could be sent from one location to another at a speed greater than c. In the reference frame of the sender, the signal travels forward in time. It is sent at time 0 and received at some later positive time, but in a reference frame moving at the appropriate velocity relative to the sender, the signal is received before it is sent. The reception event occurs at a negative time relative to the sending event. This is not a matter of optical illusions or signal delays. The temporal ordering of the two events, sending and receiving, is genuinely different in different reference frames if the signal travels faster than c. In some frames, the reception precedes the sending. The signal travelled backward in time. A single faster-than-light signal is strange enough. But the real problem becomes apparent when two parties, conventionally called Alice and Bob, use faster-than-light signals to communicate with each other. Alice sends a signal to Bob faster than light. Bob, in his reference frame, receives the signal before Alice sent it. Bob then sends a reply to Alice, also faster than light. Alice receives the reply before Bob sent it, which is before Alice sent her original message. Alice receives Bob's reply before she sends her original message. She then decides, based on the reply, not to send the original message. She receives a reply to a message that was never sent. The causal loop, a sequence of events that is its own cause and its own effect, is closed. Causality is violated. This causality violation does not arise from the specific mechanism by which the faster-than-light signal is sent. It arises from the geometry of spacetime, from the combination of Lorentz symmetry and the existence of events with space-like separations. Any signal that connects space-like separated events, any signal travelling faster than CE, can be used to construct a causal loop in the spacetime geometry of special relativity. The prohibition on faster-than-light information transmission is therefore not a property of any specific physical mechanism. It is a consequence of the structure of spacetime itself, enforced by the impossibility of consistent causality in the presence of faster-than-light signals. For the hidden limit question, the causality argument is important in two ways. First, it explains why the maximum speed of information transmission, the causality speed, must be invariant across all reference frames. If the causality speed varied in any way, if it were direction-dependent, frame-dependent, or energy-dependent in a way that could be exploited to construct causal loops, causality would be violated in the way just described. The causality requirement places strong constraints on how any energy dependence of the photon speed can be structured. The energy dependence must be such that the maximum speed of any physical influence remains invariant, even if the speed of specific photons varies with energy. Second, the causality argument illustrates that the speed of light is not merely an interesting physical constant, it is the guardian of the consistent temporal ordering of the universe. Any theory of quantum gravity that modifies the effective speed of photon propagation must preserve this guardian role, must ensure that no modification of photon speeds enables the construction of causal loops or the transmission of information to the past. Theories that satisfy this requirement can produce observable energy-dependent photon speeds while preserving causality. Theories that do not satisfy it are not merely in tension with experiment, they are self-contradictory. Quantum entanglement is often cited as evidence for faster-than-light connections between distant particles. A pair of particles is prepared in an entangled quantum state, a state in which the particles share correlations that cannot be described by any combination of independent properties of the individual particles. When one particle is measured and found to have a specific property, a specific spin direction, a specific polarization, the other particle, no matter how far away, is instantly found to have the corresponding correlated property when measured. The correlation appears instantaneous, regardless of the separation between the particles. In an experiment where the two measurements are made simultaneously, or nearly so, the correlation is established without any signal having time to travel from one particle to the other at the speed of light or below. The correlation seems to defy the speed limit. It does not. The resolution of this apparent paradox is one of the most important results in the interpretation of quantum mechanics, and understanding it precisely reveals something deep about what the speed of light actually limits. The key observation is that neither Alice, who measures her particle, nor Bob, who measures his, has any control over the outcome of their measurement. When Alice measures a quantum particle in a superposition of spin up and spin down, the result, spin up or spin down, is random. Quantum mechanics is irreducibly probabilistic at the level of individual measurements. Alice cannot decide in advance which result she will get. She gets a random result. The randomness is not a reflection of incomplete knowledge. It is a fundamental feature of quantum mechanics. When Bob measures his entangled particle, he also gets a random result. The correlation between their results, that Alice's up corresponds to Bob's down, for example, is a property of the joint state of the pair, not of the individual particles. The correlation is genuinely non-local. It cannot be explained by any local hidden variable theory, by any model in which each particle carries predetermined values for all possible measurements, values set at the moment the particles were created. John Bell proved this in 1964, and numerous experiments since, most definitively in the loophole-free Bell tests of 2015, have confirmed that the correlations between entangled particles violate Bell's inequalities and cannot be explained by any local hidden variable theory. The non-locality of quantum mechanics is real, but the non-locality does not permit faster-than-light communication. Alice's measurement result is random. Bob's measurement result is random. The correlation between them is revealed only when they compare their results through a classical channel, a phone call, a radio signal, an email, that travels at or below the speed of light. Until that comparison is made, neither Alice nor Bob knows that a correlation exists. Bob's measurement result looks completely random to him, and gives him no information about Alice's result or about whether Alice has even performed a measurement. The correlation contains no information that can be extracted by either party individually. The information is in the correlation, and the correlation can only be accessed by classical communication. This resolution, that quantum correlations are real and non-local but do not permit faster-than-light information transmission, is known as peaceful coexistence. Quantum mechanics and special relativity coexist with null conflict because the non-local correlations of quantum mechanics cannot be exploited to violate the causal structure that special relativity imposes. The non-local correlations are established instantaneously across any distance, but they carry no information that can be used. They are a feature of the mathematical structure of quantum mechanics that has no classical analogue and no classical explanation, but they respect the one requirement that special relativity enforces without exception. No information travels faster than light. What quantum entanglement reveals about the hidden limit is a boundary condition that any modified theory of physics must respect. The energy-dependent photon speed predicted by quantum gravity theories is not a violation of the causality bound. It does not allow information to travel faster than c. The modification is to the speed of specific photons of specific energies, not to the maximum speed of any physical influence. The causality structure of spacetime is preserved in these theories, even as the photon speed varies with energy, because the maximum speed of causal influence, the speed at which information can propagate, remains c or below. The hidden limit, if it exists, is a modification of photon dynamics within the causal structure, not a violation of the structure itself. Quantum entanglement, which itself exists within the causal structure while superficially appearing to transcend it, offers an analogy. Correlations that seem to violate the limit, understood properly, do not. An energy-dependent photon speed that seems to violate Lorentz invariance, understood properly within the right theoretical framework, may similarly preserve the deeper principles even while modifying their photon-specific manifestation. The black hole information paradox is one of the most consequential unresolved problems in theoretical physics, and it sits at the precise intersection of the two domains that quantum gravity must unify: general relativity, which predicts black holes and their event horizons, and quantum mechanics, which demands that information is never truly lost. Understanding the paradox, and why it cannot be resolved without physics beyond both current theories, is essential for appreciating why black holes are the most important natural laboratories for the hidden limit on the speed of light. In general relativity, a black hole forms when a sufficient concentration of mass or energy warps spacetime so severely that the escape velocity at some surface, the event horizon, equals the speed of light. At the event horizon, the geometry of spacetime reaches a critical configuration. The forward light cones, the set of spacetime directions accessible to any future moving signal, tip over entirely so that every future directed path from a point at or inside the horizon leads inward toward the singularity at the black hole's center, rather than outward toward the exterior. Light itself cannot escape from below the event horizon, not because some force pulls it back, but because the geometry of spacetime leaves it no outward direction to go. The future, from any point below the horizon, points entirely inward. This geometric picture of the event horizon is what makes the information paradox so sharp. Matter and information fall into a black hole and cross the event horizon. In classical general relativity, what falls in is lost forever. The interior of the black hole is causally disconnected from the exterior, and no signal from the interior can ever reach an observer outside. The information about the quantum state of the infalling matter, which particles it consisted of, what their quantum numbers were, how they were entangled with other particles that remained outside, becomes permanently inaccessible to any external observer. This appears to destroy information. In quantum mechanics, the destruction of information violates a fundamental principle: unitarity. The unitary evolution of quantum mechanics is time reversible in principle. If the complete quantum state of a physical system at one time is known, the quantum state at any other time, past or future, can in principle be calculated. This is not merely a practical statement about what can be computed. It is a structural requirement on the equations of quantum mechanics. The equations must map any initial state to a unique final state and vice versa, with no many-to-one or one-to-many mappings that would destroy information. Unitarity is the quantum mechanical expression of the conservation of information. Black holes apparently violate unitarity. The quantum information about the infalling matter enters the black hole and, in the classical picture, is lost. Hawking radiation, the thermal radiation that black holes emit through quantum processes near the event horizon, carries energy away from the black hole and eventually causes it to evaporate completely. But in Hawking's original calculation, the radiation is perfectly thermal, carrying no information about what fell in. When the black hole is completely evaporated, the information is gone and unitarity is violated. This is the paradox. The resolution of the paradox requires physics beyond both general relativity and standard quantum mechanics, precisely the physics of quantum gravity. Several proposals have been made. The firewall proposal, put forward by Almheri, Marolf, Polkinski and Sully in 2012, suggests that the event horizon of a sufficiently old black hole is not the featureless empty surface that classical general relativity predicts, but is instead a wall of very high-energy Hawking radiation that destroys any infalling observer. The information is not lost, it is encoded in the Hawking radiation, but the smooth experience of crossing the event horizon that general relativity predicts does not occur. The proposal replaces one paradox with another. The conflict between the equivalence principle and unitarity is made explicit rather than hidden. The holographic approach, embodied in the anti-de Sitter/conformal field theory correspondence discovered by Juan Maldacena in 1997, suggests that the information is preserved in the Hawking radiation through a mechanism too subtle for either classical general relativity or standard quantum field theory to see. In the holographic picture, the physics of the black hole interior is dual to physics on the boundary of the surrounding spacetime, and information that seems lost from the interior perspective is preserved in a scrambled form on the boundary. The resolution requires that the smooth spacetime geometry of the interior and the behavior of light within it are modified at or near the event horizon in ways invisible to classical physics but essential to quantum gravity. In every proposed resolution of the information paradox, the behavior of light near the event horizon, the behavior of the quantity C at the regime where the geometry of spacetime becomes extreme, plays a central role. The hidden limit and the information paradox are not separate mysteries. They are different windows into the same deep incompleteness of current physics. In 1974, Stephen Hawking published a calculation that changed the understanding of black holes and of the relationship between quantum mechanics and gravity permanently. The calculation showed that black holes are not perfectly black. They emit radiation. The radiation is thermal, it has a specific temperature, inversely proportional to the mass of the black hole, and it carries energy away from the black hole, causing it to lose from mass and, over an enormous timescale, evaporate completely. This result, known as Hawking radiation, was derived using quantum field theory in a curved spacetime background, a semi-classical approximation in which the spacetime geometry is treated classically, according to general relativity, while the matter fields propagating through it are treated quantum mechanically. The result was unexpected, controversial when first published, and is now regarded as one of the most important theoretical results in the history of physics. The mechanism of Hawking radiation is one of the most frequently discussed results in popular science, but its precise physical interpretation remains more subtle than common accounts suggest. The standard description in terms of virtual particle-antiparticle pairs appearing at the event horizon, and one member falling in while the other escapes, is a heuristic that captures some aspects of the physics, but is not a precise account of the calculation. The precise account involves the definition of the quantum vacuum in curved space-time, specifically the fact that different observers in different states of motion define the concept of the vacuum differently. An observer freely falling into a black hole sees the vacuum state of quantum fields as empty, no particles. An observer hovering at a fixed distance from the black hole, using rockets to maintain their position, sees the same quantum state as containing a thermal bath of particles at the Hawking temperature. The radiation that a distant observer receives as the black hole evaporates is a consequence of this observer dependence of the vacuum state in curved spacetime. The Hawking temperature of a black hole is given by a simple formula. T equals the reduced Planck constant times c cubed divided by 8 pi times g times m times the Boltzmann constant, where m is the black hole mass. For a stellar mass black hole of 10 solar masses, this temperature is approximately 6 times the 10 to the negative 9 Kelvin, far colder than the cosmic microwave background temperature of 2.7 Kelvin. The Hawking radiation from such a black hole would be completely swamped by the microwave background and is utterly undetectable. For a black hole of 1 solar mass, the temperature is 6 times 10 to the negative 8 Kelvin. Even if the cosmic microwave background were absent, even in a hypothetically cold universe, detecting Hawking radiation from any astrophysical black hole would be impossible with any conceivable instrument. As black holes lose mass, they heat up. A black hole losing mass through Hawking radiation radiates at a higher temperature as it becomes lighter, which causes it to radiate even faster, which causes it to lose mass even faster, a runaway process that accelerates as the black hole shrinks. The lifetime of a black hole before complete evaporation scales is the cube of its initial mass. A stellar mass black hole would take approximately 10 to the 74th years to evaporate, a time span that makes the current age of the universe, approximately 10 to the 10 years, seem negligible. A black hole of 1 kilogram would evaporate in approximately 3 times 10 to the negative 22nd seconds, a tiny fraction of a femtosecond. The most theoretically interesting scenario for the hidden limit is the evaporation of a black hole with mass approximately equal to the Planck mass approximately 2 times 10 to the negative 8 kilograms. Such a black hole, if it exists, has a Schwarzschild radius approximately equal to the Planck length and a Hawking temperature approximately equal to the Planck temperature, approximately 1.4 times 10 to the 32nd Kelvin. This is the highest temperature that current physics can describe, the temperature at which the quantum geometry of spacetime becomes important, and the semi-classical approximation used to drive Hawking radiation breaks down completely. A Planck mass black hole evaporating at the Planck temperature releases all of its mass energy in approximately the Planck time, approximately 5 times 10 to the negative 44th seconds, in a burst of radiation at the Planck energy. At the Planck temperature and Planck energy, the hidden limit, the energy-dependent modification to the speed of light, is not a small perturbation. It is an order unity effect. The propagation of light near a Planck mass evaporating black hole is governed by whatever theory of quantum gravity is correct, not by the approximation of smooth spacetime and constant c. Understanding this final stage of black hole evaporation requires quantum gravity in the same way that understanding the final stages of an atom's collapse requires quantum mechanics. The semi-classical approximation breaks down precisely where the physics becomes most interesting, and the hidden limit on the speed of light is one of the quantities that reveals its true nature at this extreme. The concept of a laboratory implies a controlled environment, a place where conditions can be set precisely, variables can be isolated, and measurements can be made with arbitrary precision. Black holes are the opposite of controlled environments in almost every practical sense. They are located at distances ranging from thousands to billions of light-years. Their interiors are causally inaccessible to any external observer. The most extreme conditions within them, the singularity at the centre, the Planck scale physics of the event horizon during the final stages of evaporation cannot be predicted by any below the event horizon. In what sense then can black holes be laboratories for the hidden limit? The answer is that the physics of black holes, even as observed from the outside to this aurora, carry signatures of Planck scale physics that can in principle be detected by external observers. This occurs through several mechanisms. The first is the gravitational wave emission from black hole mergers. When two black holes merge, a process that has been observed by the LIGO and Virgo gravitational wave detectors beginning in 2015, they emit an enormous burst of gravitational radiation that propagates through spacetime and can be detected at cosmological distances. The characteristics of this gravitational wave signal depend on the properties of the black holes and on the behavior of spacetime near the event horizons during the merger. If Lorentz invariance is violated at Planck energies, the propagation speed of gravitational waves of different frequencies may be slightly different, producing a frequency-dependent arrival time pattern analogous to the photon time delays searched for in gamma-ray burst observations. The first gravitational wave detection from a binary neutron star merger, GW 170817, detected in August 2017, was accompanied by a short gamma-ray burst that reached Earth approximately 1.7 seconds after the gravitational wave signal. This multi-messenger observation provided an extraordinarily precise constraint on the relative speed of gravitational waves and photons. If the two signals were emitted simultaneously or nearly so, and the 1.7 second delay is attributed to the difference in emission time rather than propagation speed difference, then the speed of gravitational waves equals the speed of light to better than 1 part in 10 to the 15th. This constraint rules out many theoretical models in which gravity and electromagnetism propagate at different speeds and places, tight limits on specific forms of Lorentz invariance violation in the gravitational sector. The second mechanism through which black holes probe Planck scale physics is the quantum emission of Hawking radiation during the final stages of evaporation. As a black hole approaches the Planck mass, its Hawking temperature approaches the Planck temperature, and the quantum corrections to the emission become order unity. The spectrum of the radiation, how many photons are emitted at each energy, departs from the perfectly thermal distribution predicted by the semi-classical approximation. The departure encodes information about the Planck scale physics governing the final evaporation. If it were possible to observe this final stage emission, which would require the existence of primordial black holes formed in the early universe and evaporating today, the spectrum would provide direct information about the modification to the photon dispersion relation at Planck scale energies. The search for primordial black holes, and for the gamma-ray signatures of their final evaporation, has been conducted by various experiments including Fermi and ground-based gamma-ray observatories. No confirmed detection has been made. Upper limits on the density of evaporating primordial black holes constrain their abundance in the current universe. But the search continues, and a detection would provide unique information about Planck-scale physics inaccessible through any other observational channel. Analog black holes represent a third, indirect approach to using black hole physics as a laboratory. An analog black hole is a physical system whose mathematical description mimics the mathematics of a real black hole, enabling laboratory study of phenomena, including the analog of Hawking radiation, that cannot be studied in real black holes. Flowing fluids in which sound waves are trapped behind a sonic horizon, Bose-Einstein condensates in which phonons are trapped in a configuration analogous to the event horizon, and optical systems in which light is trapped in a medium with a gradient refractive index. All of these have been used to observe analogues of the Hawking effect and to study the physics of the analog horizon. The analog systems cannot replicate Planck-scale physics since they operate at entirely different energy scales and are described by different fundamental equations, but they test aspects of the Hawking mechanism that are shared between the analog and real systems and thereby build confidence in the theoretical framework that predicts the real effect. The study of analog black holes is one component of a broader program of understanding the interface between quantum mechanics and the physics of horizons, the interface where the hidden limit on the speed of light has its deepest expression. The holographic principle is among the most counterintuitive and far-reaching ideas in modern theoretical physics, and it emerged not from abstract speculation, but from a careful analysis of the thermodynamics of black holes. It proposes that the complete physical description of any region of space is encoded not in the volume of that region but on its boundary surface, that the three-dimensional physics of an interior is exactly equivalent to the two-dimensional physics of its surrounding surface, in the same way that a hologram encodes a three-dimensional image on a two-dimensional photographic plate. If the holographic principle is correct, the three-dimensional world we inhabit is in some precise mathematical sense a holographic projection of physics occurring on a two-dimensional surface that surrounds it. The path to this extraordinary proposal begins with the thermodynamics of black holes. In the early 1970s, Jacob Bekenstein, then a graduate student at Princeton, argued that black holes must have entropy, a thermodynamic quantity that measures the number of ways a system can be arranged internally while appearing the same from the outside. The argument was based on the observation that if black holes had no entropy, the total entropy of the universe could be decreased by throwing entropic matter into a black hole, violating the second law of thermodynamics. The entropy of a black hole, Bekenstein argued, must be proportional to the area of its event horizon rather than to its volume. This was a striking proposal. Entropy is normally an extensive quantity, proportional to the volume of a system. Bekenstein was saying that for black holes, entropy scales with area. Hawking's calculation of black hole radiation confirmed and quantified this proposal. The entropy of a black hole is equal to 1/4 of the event horizon area measured in Planck area units, 1 bit of information per 4 Planck areas of horizon surface. This formula, known as the Bekenstein-Hawking entropy, has passed every consistency check that has been applied to it, and is now considered one of the most reliable results in quantum gravity, even though it was derived without a complete theory of quantum gravity. The profound implication of the Bekenstein-Hawking entropy formula is that the maximum entropy, and therefore the maximum information content, of any region of space is determined not by the volume of the region but by the area of its boundary, with 1 bit of information per 4 Planck areas of boundary surface. This is the holographic bound, and it applies not just to black holes, but to any physical system. A volume of space cannot contain more information than this bound allows. If it tried to, the information density would be so high that the region would collapse into a black hole. The holographic bound is therefore a fundamental limit on how much physical reality can be packed into a given volume of space. In 1997, Juan Maldacena at the Institute for Advanced Study in Princeton made this informal holographic principle precise in a specific theoretical context. He showed that a specific theory of quantum gravity in a 5-dimensional anti-de Sitter spacetime is exactly equivalent, dual, to a specific quantum field theory without gravity on the 4-dimensional boundary of that spacetime. The two descriptions contain the same physical information, expressed in completely different mathematical languages. The 5-dimensional bulk theory includes gravity and curved spacetime. The 4-dimensional boundary theory has no gravity and exists on a flat spacetime. Every question that can be asked in the bulk has an equivalent answer in the boundary, and vice versa. The two descriptions are different languages for the same reality. For the hidden limit on the speed of light, the holographic principle has implications that go to the heart of what C actually is. If the 3-dimensional spacetime that physics describes is a holographic projection of 2-dimensional boundary physics, then the properties of that 3-dimensional spacetime, including the speed of light, are not fundamental properties of reality. They are emergent properties of the holographic projection. The speed of light in the bulk, the 4-dimensional spacetime we observe, is determined by the dynamics of the boundary theory, which has its own structure and its own characteristic energy scales. If the boundary theory has a natural energy scale analogous to the Planck scale, a scale at which the boundary dynamics become non-perturbative or qualitatively different, the projection of the boundary behavior into the bulk might produce an energy-dependent modification to the speed of light, even if the boundary theory itself has no concept of a fundamental C. The holographic principle does not predict the hidden limit. It provides a theoretical framework in which the hidden limit would arise naturally as a consequence of the emergent nature of spacetime rather than as an additional assumption. Whether the specific holographic framework that describes our universe produces a detectable modification to the speed of light at accessible energies is a question that cannot currently be answered, because the specific dual description of our universe, if one exists, is not known. But the holographic principle has shifted the conceptual landscape. The question is no longer whether C could be emergent, but what the specific emergent mechanism is. The word emergent carries a specific meaning in physics that distinguishes it from mere complexity. An emergent phenomenon is one that is not present in the fundamental description of a system, but appears at a macroscopic level as a consequence of the collective behavior of many fundamental constituents. Temperature is emergent. It is not a property of any individual molecule, but it emerges from the collective kinetic energy of many molecules in a gas. Sound is emergent. It is not a property of any individual atom in a solid, but it propagates through the solid as a collective oscillation of many atoms. Superconductivity, magnetism, and the rigidity of solids are all emergent. They arise from the quantum mechanical collective behavior of electrons and ions in ways that could not be predicted simply by examining a single electron or ion in isolation. The possibility that the speed of light is emergent is the possibility that C, like temperature, like sound, like superconductivity, arises not from a fundamental property of the universe at its deepest level, but from the collective behavior of whatever fundamental constituents make up the fabric of space-time itself. This is a radical idea. Everything in physics, from electromagnetism to quantum mechanics to general relativity, uses C as a given, a primitive constant built into the equations from the beginning. To say that C is emergent is to say that the equations themselves are approximations, valid in a regime where the fundamental constituents are so numerous and so fine-grained that their collective behavior produces a smooth, continuous spacetime in which C is a well-defined constant, but breaking down at the scales where the individual constituents are resolved. The best developed analogue for this picture comes from condensed matter physics, specifically from the study of quantum critical phenomena. Near a quantum critical point, a phase transition that occurs at zero temperature, as some parameter is varied, certain systems of electrons or other quantum particles develop collective behavior described by quantum field theory, with exact Lorentz invariance and a specific maximum speed. This Lorentz invariance is emergent. The underlying lattice of ions has no Lorentz symmetry whatsoever. It has discrete translational symmetry, not continuous Lorentz symmetry. But at low energies and long distances near the quantum critical point, the effective description of the electrons becomes exactly Lorentz invariant, with an emergent speed that plays the role of C in the effective theory. Above some energy scale set by the lattice spacing, the analogue of the Planck scale, the emergent Lorentz invariance breaks down and the underlying lattice physics becomes relevant. If space-time is a quantum system with its own microscopic structure, as suggested by loop quantum gravity, causal set theory, and the holographic principle, it might exhibit exactly this kind of emergent Lorentz invariance. The smooth, continuous space-time of general relativity would be the low-energy, long-distance description of a system whose microscopic structure is very different from a smooth manifold. The speed of light would be the emergent maximum speed of this low-energy description, accurate at every scale that has been probed experimentally, but modified at the microscopic scale where the underlying structure becomes relevant. Under this picture, asking what C is really, what determines its value and why it has the specific value it has rather than any other, is answered not by pointing to any fundamental property of light or space-time, but by asking what the microscopic structure of space-time is and how its collective behavior produces the emergent Lorentz invariance with the specific emergent speed that is observed. This is analogous to asking why the speed of sound in diamond is approximately 12 kilometers per second. The answer is not found in any fundamental property of sound, but in the atomic structure of diamond and the force constants of the chemical bonds between carbon atoms. The speed of sound is determined by the microscopic structure of the medium through which it propagates. If C is emergent, it is determined by the microscopic structure of the medium through which everything propagates, space-time itself. The experimental evidence for the emergence of C is currently absent. No measurement has detected the breakdown of Lorentz invariance that would signal the scale at which the emergent description fails and the fundamental structure becomes visible. The current constraints from gamma-ray burst timing, cosmic rays, and gravitational wave observations tell us that if C is emergent, the emergent scale is at or above the Planck energy, that the effective Lorentz invariance is accurate at all energies below the Planck scale by at least the precision of current observations. This is consistent with the emergent picture, since the Planck scale is precisely where the emergent description would be expected to break down. The measurements confirm the prediction of the emergent picture, that no deviation should be seen below the Planck scale, but they cannot yet probe the scale at which the deviation is predicted to appear. The question of whether C is emergent is the question of what spacetime is at its most fundamental level. It is the deepest question in contemporary physics, and its answer, if it is eventually obtained, will transform the understanding of every equation that contains C. The experimental situation for the hidden limit is one of the most interesting in contemporary physics. The theoretical framework is developed enough to make specific predictions. The observational technology has reached a level of sensitivity where some of those predictions can be tested, and the next generation of instruments promises to extend the reach of the tests by factors of 10 to 100 in sensitivity. Whether these improvements will be sufficient to detect the hidden limit, if it exists at the level predicted by the most optimistic quantum gravity models, is an open question. Whether they will be sufficient to rule it out definitively at the Planck scale, if it does not exist or is suppressed below the Planck energy scale, is also open. What is certain is that the next decade will see the observational program for the hidden limit advance substantially. The Cherenkov Telescope Array Observatory is the most significant upcoming development for gamma-ray-based tests of the hidden limit. The CTA is a ground-based observatory consisting of 2 arrays of imaging atmospheric Cherenkov telescopes, one in the northern hemisphere at La Palma in the Canary Islands, and one in the southern hemisphere at Paranal in Chile. Atmospheric Cherenkov telescopes detect the faint flashes of blue Cherenkov light produced when very high-energy gamma rays strike the upper atmosphere and produce air showers, allowing reconstruction of the energy and arrival direction of the primary gamma ray. The CTA will detect gamma rays from approximately 20 giga-electron volts to more than 300 tera-electron volts, a range extending to much higher energies than the Fermi Large Area Telescope, with a sensitivity roughly 10 times greater than any existing ground-based gamma-ray observatory. For gamma-ray burst observations, the CTA's primary advantage is its sensitivity at energies above 100 giga-electron volts. Fermi's Large Area Telescope has detected only a handful of photons above 10 giga-electron volts from gamma-ray bursts in over 15 years of operation, because the flux of very high-energy photons from bursts at cosmological distances is extremely low, and the Fermi collection area is limited. The CTA, with its much larger collection area, will detect substantially more high-energy photons per burst from the small fraction of gamma-ray bursts that are observable by ground-based telescopes. For favourable bursts at redshifts accessible to optical follow-up, those at moderate distances with bright X-ray afterglows, the CTA expects to detect tens to hundreds of photons above 10 giga-electron volts, dramatically improving the statistical power of time delay measurements. The square kilometre array represents a comparable advance for radio frequency tests of the hidden limit. The SKA is being constructed in South Africa and Australia, and will eventually comprise thousands of individual radio antennas distributed over distances of up to 3,000 kilometers, providing a combined collecting area of approximately 1 square kilometer, about 50 times the collecting area of the most sensitive existing radio telescope arrays. For pulsar timing tests of Lorentz invariance, the SKA will detect radio emission from pulsars with signal-to-noise ratios far greater than any existing instrument, enabling timing precision at the level of tens of nanoseconds for the best pulsars. It will also discover thousands of new millisecond pulsars, dramatically expanding the sample available for timing array analyses. The improved timing precision and expanded pulsar sample will sharpen the constraints on frequency-dependent propagation from radio observations by roughly an order of magnitude. In the gravitational wave sector, the Laser Interferometer Space Antenna, LISA, represents the most significant upcoming advance. LISA is a space-based gravitational wave observatory consisting of 3 spacecraft in a triangular formation separated by approximately 2.5 million kilometers, scheduled for launch by the European Space Agency in the early 2030s. LISA will detect gravitational waves at frequencies between approximately 1 MHz and 100 MHz, a range complementary to the 10 to 1000 Hz range of ground-based detectors like LIGO and Virgo. The low-frequency range accessible to LISA includes gravitational waves from supermassive black hole mergers at cosmological distances and from inspiraling white dwarf binary systems in the Milky Way. The detection of gravitational wave signals from supermassive black hole mergers at high redshift, combined with electromagnetic counterparts from the same events, will allow multi-messenger tests of gravitational wave propagation at vastly greater distances than GW 170817, and with much better constraints on any speed difference between gravitational waves and photons. Combined, the next generation of observational instruments, CTA for gamma rays, SKA for radio, LISA, and next-generation ground-based detectors for gravitational waves and improved cosmic ray observatories for ultra-high-energy particles, will constrain the hidden limit across every observational channel simultaneously. The constraints will be complementary rather than redundant, probing different energy scales, different propagation distances, and different physical processes. If the hidden limit exists at any level accessible to these instruments, the cumulative constraints from all channels will eventually reveal it. If it does not exist at those levels, the cumulative null results will establish that the speed of light is constant to a precision that no current observation can achieve, a confirmation of special relativity at depths Einstein never imagined testing. Something remarkable happens when you stand at the edge of what physics knows and look at the distance between that edge and the territory that lies beyond. The distance is not a gap in data, not a shortage of funding, not a failure of ingenuity. It is a structural feature of the universe, a gulf between the scales accessible to human measurement and the scales where the deepest questions have their answers. The speed of light sits at the center of this gulf. It is the most measured, most confirmed, most deeply embedded constant in all of physics. It is also the constant whose deepest nature has never been confirmed, because confirming it would require probing scales at which no instrument yet built, or easily imagined, can reach. The history of physics prepares us for this situation, even as it offers no guarantee of how it will resolve. Absolute time, the foundational assumption of Newtonian mechanics, unchallenged for more than 2 centuries, turned out to be a low-velocity approximation to the relative time of special relativity. The Euclidean geometry of space, accepted since ancient Greece, formalized by Newton, taken as a priori necessary by Kant, turned out to be a low-curvature approximation to the Riemannian geometry of general relativity. The continuous fluid of classical thermodynamics, the perfectly natural description of any flowing substance, turned out to be a large-scale approximation to the behavior of discrete molecules. The smooth electromagnetic field of classical electrodynamics, described by Maxwell's equations with such precision that no classical physicist doubted its fundamental nature, turned out to be a large-scale approximation to the quantum electrodynamics of discrete photons and electron-positron pairs. Each transition in this sequence has the same structure. A quantity that was taken to be fundamental, exact, and universal turned out to be emergent, approximate, and domain-specific. The quantity was not wrong in any useful practical sense. It remained useful within its domain of applicability, but it was superseded, explained, derived from something deeper that contained it as limiting case. And in each case, the transition to the deeper description revealed a richer, more intricate picture of reality, one that would not have been guessed from within the approximation itself. The speed of light, at its current level of experimental confirmation, fits the pattern of quantities waiting for this transition. It has been measured with extraordinary precision within its domain of experimental accessibility. All energies below the Planck scale, all distances above the Planck length, all gravitational fields weaker than those near the event horizons of known black holes. Within this domain it is constant. The measurement is not in doubt. But the domain is not all of physics. It does not include the Planck scale, the early universe within the first Planck time of the Big Bang, or the physics at the centre of a black hole. It does not include the regime where quantum mechanics and gravity must both be applied simultaneously. It does not include the regime where the fundamental structure of space-time, if it has a fundamental structure beyond the smooth manifold of general relativity, would become apparent. The hidden limit explored throughout this video is not a confirmed result. It is a prediction of a class of theoretical frameworks motivated by the need to unify quantum mechanics with general relativity, that has not yet been confirmed or definitively ruled out by observation. The current observational constraints from gamma-ray burst timing, cosmic ray spectra, pulsar timing, and gravitational wave propagation have ruled out the most optimistic versions of the prediction. Linear Lorentz invariance violation at or above the Planck scale for photons propagating in the subluminal direction has been excluded by GRB 090510 and subsequent observations. What remains open is the possibility of superluminal linear violation, quadratic violation of either sign, and any modification suppressed below the Planck scale. The next generation of instruments will probe some of these remaining possibilities with substantially improved sensitivity. The question of whether these future observations will detect the hidden limit is one that cannot be answered from within the current state of knowledge. It is possible that they will. It is possible that the effect is real, at the level of quadratic Lorentz invariance violation suppressed by the Planck energy squared, and that the Cherenkov telescope array will eventually accumulate enough high-energy photons from enough gamma-ray bursts to detect it statistically. It is equally possible that they will not, that the speed of light is constant to a precision exceeding the sensitivity of any foreseeable instrument, and that if there is a hidden structure to see, it lies beyond reach of observation for the foreseeable future. What is not possible is to stop asking the question. Physics advances by testing its most comfortable assumptions at their boundaries. The speed of light is the most comfortable assumption in all of physics, and its boundary, the Planck scale, is the most important untested regime in all of science. The constant that built modern physics may turn out to have been a limit all along, not a limitation of the universe, a limit of the description. And what lies beyond the description is where physics, always and without exception, eventually goes.